Our next step is to evaluate the sentiment model that we've built. Now, we just talked in this module about classification error, precision, false positives and false negatives, and we're going to explore that idea right here in this demonstration in this notebook. So, the sentiment model has a function called evaluate, and that function evaluate allows you to evaluate its quality on some test data, and we're going to provide a particular metric, and this metric is called the ROC curve, and we're going to learn a little bit more about the ROC curve next. But the ROC curve is a way to explore the false positives and false negatives and that confusion matrix that we discussed. Now here it shows you the results of the evaluation. It's a little hard to see in text, so let's do a little visualization of it, again using Canvas. So we can use sentiment model dot show, and what we're going to show, the view that we're going to use is going to be the evaluation view. And here we go. Okay, now this is really cool. We've built a few things. So this is a precision recall. This is a ROC, what's called a ROC curve. Is a curve that trades off false positives with true positives. Let me explain that a little bit. But first, let's look at these numbers over here. So this is the confusion matrix. The number of true positives, the things that we got right, that were true, is 26,455. So right here. The number of true negatives was only 4,000, so 3,965. So this is a highly unbalanced case. And then the number of false positives and the number of false negatives is about the same. The overall accuracy was 91.1%, so 0.911. And we also discussed a few metrics like precision recall and F1 score, which we're going to learn more about later in the course and later in the specialization. Now, the thing about the false positives and false negatives is that there is a very natural way to change the threshold of what we believe the transition from negative class to positive class should be. So, and this is what this threshold shows on the right. But let me first show it on the curve here. So you can see it is possible for me to get, for example, a very high true positive rate, so 0.4, a very low 0.4, if I don't allow myself to get any false positives. So if I'm very worried about false positives, I can be very conservative, get no false positives, but again, not capture many of the true positives and make other mistakes. And you see, as you go through the curve, there's a kink here. This is the point where you get not too many false positives, but a lot of true positives. And then over on this end, you get every true positive, but you get a lot of false positives. How do you get every true positive, but get a lot of false positives? You just say every data point is positive. Then you get all the true positives, but you also make a lot of mistakes. And we'll discuss more of this when we talk about the precision recall curve. But nicely, you can change the threshold over here and walk that curve up there, as you can see. And so, for example, at the far end on the right, you see that the true positive rate is really high. There's no false positives, but there's no true negatives. So there's no false negatives, no true negatives. You just got everything right. And then you can slide it just the other way. So you can play with this and really kind of get a good sense of what this curve really means, the ROC curve. And that's the evaluation that we're going to be doing. We've built a model. We understood its accuracy about 0.911%. Let's go and actually use this model for something actually quite cool. So what I'm going to do is apply the model, learned model, to understand sentiment for our friend the giraffe. So here we go. Let's understand it a little bit. So here's what I'm going to do. I'm going to take those giraffe reviews that I built a little bit earlier, and I'm going to create a new column to this giraffe reviews called my predicted sentiment. And this predicted sentiment is going to come from taking the sentiment model that we built, the sentiment model, and oops, this autocomplete was a little slow, sorry about that. We have a little glitch there. So, okay. We're going to take the sentiment model and we're going to call this function predict on it. And we're trying to predict how does it feel about the giraffe reviews. So how do you feel about, my friends, the giraffe reviews? And the output, and this is a key thing, we're not just going to output the 0, 1, whether I predict the sentiment to be 0 or 1. I'm going to say output probability. And if you remember, we just talked about this in the module, that by outputting probability, you can get a more fine-grained estimate of what the prediction looks like. So we just ran it, and just let's take a quick look at what this new giraffe reviews look like. So let's look at the head of this table. And you'll see that now we had the name of the product, the review, the rating, the word count, and I added another column called the predicted sentiment. And for some reviews, it's really high, 0.999, 0.99. And here's a review that's pretty low sentiment. There should really be a large warning on the they don't like it for some reason. Now let's try to understand. Let's look at the reviews and see what reviews are positive or negative. And let's see what the people are saying about the product. So here's what I'm going to do. We're going to sort the reviews based on the predicted sentiment and explore. And the cool thing here is the predictive sentiment is a much more fine-grained description of whether a review is positive or negative. The stars are really skewed, 5 stars, 4 stars, 3 stars, 1 star, but it doesn't tell you how far along the spectrum you are. But now that we have these numbers, this extra column, we can do a lot more. So I'm going to take this giraffe data and I'm going to sort it. So all I have to do is take the same value, and I'm going to call the function sort on it, and you have to say what column you're sorting based on. So we're going to sort based on this new column that we called predicted sentiment. And one little trick here, we're going to say ascending is equal to false. So instead of sorting that ascending order, it's going to sort in descending order, starting from the most positive reviews down to the most negatives. Now that we've sorted it, we're going to just show the first few lines of the table, and what you should see is that the reviews are now sorted based on that sentiment. So the very top here, we have the most positive one has predicted sentiment of 1.999, and they're all sorted. So for that first review, they had product sentiment predicted as 1. Let's take a look at that review. So I'm going to look at the giraffe reviews. The first one is 0, the index 0, and let's look at the actual text of the review. Okay, I'm going to read this to you a little bit. It says, "Sophie, oh Sophie, your time has come. My granddaughter Violet is 5 months old and starting to teeth. What a joy for little Sophie. Little Sophie brings Violet." Oh, Violet really loves Sophie. "Sophie is made very pliable rubber that is sturdy but not tough, and it's quite easy for Violet to twist unheard positions and put it in her mouth." And Okay, that's what a positive review looks like. She's writing a poem about Sophie. Let's look at the second positive review here. So this is the for element 1, so it's the second element on the table, and let's look at what that review looks like. And here's what it says. I'm not sure why Sophie is such a hit with the little ones, but my 7-month-old baby girl is one of the adoring fans. The rubber is softer and pleasant to handle. My daughter enjoys chewing on it, on the legs, nubs of the head, so these ears get chewed, and so on. She really loves it, and it loves that it's squeaky. So apparently it's a big hit. So this is 2 positive reviews. Now let me show you a little Python trick which we can use to show the most negative reviews. So the most negative reviews are at the bottom of the table. So we could ask what is the length of the table and find the last element and so on. But with Python, we can do this really easily. So let me show you what's happening next. Show most negative reviews. So we can take this table and just index it with a negative number, -1. And what that does, it goes to the end of the table. So -1 is the last element, -2 is the second to last element, and so on. So let's look at the most negative review for our giraffe. And I forgot to put a quotes here. So let's just do that. And execute. Okay. Here's a negative review about poor Sophie. My son loved Sophie. I bought one for every baby shower I've gone to. Now my daughter, 6 months old, just today nearly choked on it. And I'll never give it to her again. So the problem is, this person's daughter is really scary, almost choked by trying to swallow this giraffe. And so you see a negative review about somebody talking about how this giraffe, which is a lovely chewing toy, is also a choking hazard. Let's look at the second most negative review. So again, giraffe, and -2, second most negative review, and we'll take a quick look at it. So one thing that people don't like about it is it might be a choking hazard. So let's see what this one says. This children's toy is nostalgic and very cute. That sounds pretty positive. Even though the second most negative review starts pretty positive. However, the distinct rubber smell and very odd taste. Yes, I tried it. So this person tried to chew his or her kid's toy that my baby did not enjoy. So apparently the rubber smells and this person wasn't able to chew it, clean it, and the kid did not like it and they overpaid for this toy. So the second thing that people complain about is that this is a smelly toy. Smells okay to me, but could be an issue. Okay, so now in a few lines of code, we build a sentiment analysis system that can actually look at reviews and really sort them and show really positive and negative aspects of this particular product.
Okay, so in this module, we're going to talk about clustering and similarity. And the point here is the fact that often we have lots of observations and we want to infer some kind of structure underlying these observations. And in this case, the structure we're going to talk about is groups of related observations or clusters. And as with all of our modules, we're going to motivate everything with a real-world application, a case study. And in this case, we're going to talk about a task of retrieving documents of interest. So the first thing we need to describe is how are we going to represent the documents that we're looking at. Okay, so perhaps the most popular model to represent a document is something called the bag of words model, where we simply ignore the order of words that are present in the document. And the reason it's called a bag of words model is we think of taking a bag, throwing all the words from that document into the bag, shaking it up, and the new document we've created with the words all jumbled up has exactly the same representation, as I'll describe, as the original document where the words were ordered. And And what we're going to do, instead of considering the structure, the order of the words, is we're simply going to count the number of instances of every word in the document. So let's look at a specific example of this. And so in this document, we're going to imagine that there's just one sentence, and that sentence says that Carlos calls the sport football, Emily calls the sport soccer. Actually, I guess that's really two sentences, but that's the entire document. And what we're going to do to count the number of instances of words in this very short document is we're just going to look at a vector, and this vector is defined over the vocabulary in whatever language we're looking at. So maybe one word in our vocabulary is the name Carlos. Another place in this vector is the index for the word sport. And then somewhere else we have the word football, luckily in our English vocabulary that I'm writing here. And then let's say Emily is this last entry. What words are we missing? We're missing the word calls, and of course the word the. Okay, so how many instances of Carlos? Well, there's only one. How many instances of the? We have 2 of the, 2 of calls, 2 of sport, 1 of football, and I forgot the word soccer, 1 word of Emily, and let's just throw soccer in here, imagining this was the index, and this would be our word count vector with, for this document, every other entry would be 0. And all these other entries represent all the other words that are out there in the vocabulary, like the word cat and dog and tree and every other word you can think of. So it's a very, very long and sparse vector that counts the number of words that we see in this document. Okay, so we talked about this representation of our documents in terms of just these raw word counts, this bag of words model. And now we want to talk about how we're going to measure the similarity between different documents, because we're going to use that in order to find documents that are related to one another. So if like we talked about before, Carlos is reading an article, what's another article he might be interested in? Okay, so imagine that this is the count vector we have for this article on soccer with this famous Argentinian player, Messi. And then there's another article here that I'm showing in blue and the associated word counts. And this article is about another famous soccer player, Pele. Is that right? Pele. So when we think about measuring similarity, what we can do is simply look at an element-wise product over this vector. So for every element in the vector, we're going to multiply the 2 elements appearing in these 2 different count vectors and add up over all the different elements in this vector. So here I've done this math where we have 1 times 3, all the other elements multiply to 0, except at some point that 5th entry in the vector, we have 5 times 2, and if we do this multiplication over the whole vector, the sum of these terms is 13. So that measures the similarity between these 2 articles on soccer. But now let's compare to another article, which happens to be something about a conflict in Africa. And so I'm providing the examples of word counts that appear in this article. And what we see is when we go to measure the similarities between these articles using the method that I described of element-wise product and then adding, that the similarity here in this case is 0. Okay, so let's talk about an issue that arises when we use these raw word counts to measure the similarity between documents. So to do this, let's look at these green and blue articles that we had before. And so I'm repeating the word count vectors that we had. And what we calculated before was the fact that the similarity between these 2 articles that are both about soccer is 13. Okay, but now let's look at what happens if we simply double the length of the documents. So now every word that appeared in that original document appears twice in this twice as long document. So the word count vector is simply 2 times the word count vector we had before. So when we go to calculate the similarity here, what we see is now the similarity is calculated to be 52. So let's think about this. What we're saying is that 2 documents that are related to each other in the same way as before. They're both talking about the same two sports, but one just is replicated twice, is a lot more similar. We would say, yes, Carlos is a lot more interested in this longer document than what happened when Carlos was reading the shorter documents. So this doesn't make a lot of sense when we're trying to do document retrieval, and it biases very strongly towards long documents. So let's think about how we can cope with this. So one solution is very straightforward, where we're simply going to normalize this vector. So we take this word count vector, and we're going to compute the norm of the vector. And so if you guys remember computing the norm of a vector, we simply add the square of every entry in the vector and then take the square root. So in this case, we have the square root of 1 squared plus 5 squared plus 3 squared plus 1 squared. And that happens to be the number 6. And so the resulting normalized word count vector is shown on the bottom of the slide here. And what this does is it allows us to place all of our articles that we're considering, regardless of their length, on equal footing, and then use this normalized vector when we go to do retrieval. So the normalized count vectors that we just described helped address some of the issues with our original proposal of just using raw word counts as our representation of the document. But there's another issue, which is often what we'd like to do is really emphasize the important words in a document. So we're going to discuss a little bit about what it means to be an important word and how we can think about emphasizing them. Okay, before we talk about important words, let's first talk about rare words. So again, let's imagine that we're reading an article about soccer, and in this article there are lots and lots of common words like the and player and field and goal. And what we mean by a common word is a word that appears frequently in the corpus. In the corpus, that's just terminology for all the documents out there that we are looking at when we're doing this task of retrieval. And what happens, though, is that these common words dominate the similarity metric that we talked about when we compare against other documents. Because, like I said, these words appear in lots and lots of documents. Whereas in contrast, there are some very rare words in this document we're looking at, words like football and Messi, the specific player we're reading about, that get completely swamped by all these common words. And these words like football and Messi, they get swamped because they just appear very infrequently in the corpus. So let's think about how to increase the importance of these rare words, because those often are the ones that are really relevant in describing what's unique about this article and what might indicate which other articles out there Carlos, for example, is interested in reading. Okay, so like we said, what characterizes a rare word is the fact that it infrequently appears in the corpus. And what we want to do is we somehow want to upweight these rare words, and equivalently to thinking about emphasizing words that appear only in a few documents, we can think about taking each word and discounting the weight on that word based on how many documents that word appears in the entire corpus. Okay, so a question is, do we really want to just emphasize the rare words? Well, we clearly don't want to emphasize the very common words, the words like the and it and everything like that. But what we want to include are things that are very relevant for that document. So not just words like Messi, but also probably soccer and field and goal, things that describe the sport that we're looking at, which might be different than even another article about sports, an article about basketball that talks about basketball, hoop, and court, and words like that. So in this case, we want to emphasize what I'll call important words, okay? And so what we're going to trade off here is we're going to think about words that appear very frequently in the document, so they're relevant to the document that we're currently reading. So I'll call this common locally. And at the same time, we want them to appear relatively infrequently in the corpus. So I'll call this rare globally. And what characterizes a quote-unquote important word is some trade-off between this local frequency and global rarity. Okay, so one way to represent this trade-off between something that's common locally but rare globally is something that's called TF-IDF, or term frequency inverse document frequency. Okay, so first let's describe what term frequency is. And here, what we're going to do is look locally. We're looking just at the document that the person is currently reading, and we simply count the number of words like we did. So this is just our word count vector. But then what we're going to do is we're going to downweight this vector based on something called the inverse document frequency. So for this, we're going to look at all documents in our corpus, and we're going to compute the following thing, which is log of the number of documents in the corpus divided by 1 plus the number of documents that contain the word that we're looking at. Okay, so let's think a little bit about why we have this form. So first, let's think about a very common word. So a word appearing in many documents. Well, what happens? We end up with the log of some large number divided by 1 plus another large number. And we'll say this is approximately log of 1, which is equal to 0. So what we see here is that we're going to be very, very strongly downweighting all the way to 0 the counts of any word that appears extremely frequently, a word that appears in all of our documents. Okay, but in contrast, if we have a rare word, we're going to have log of, let's say, a large number, assuming we have a large number of documents that we're searching over, divided by 1 plus a small number. And this is going to be, I'll just say, some large-ish number, or a not 0 or small number. And the reason that we have this 1 here is the fact that we can't assume that every word appears in any document in the corpus. So there might be some word in the vocabulary that doesn't appear anywhere in our corpus, and so we want to avoid dividing by 0. Okay, so let's look at an example where there's the index for the word the, and let's say that the appears, I don't know, something like 1,000 times in the document that I'm looking at. And then there's the word messy. Messy appears 5 times. Okay, now I'm going to look at computing the inverse document frequency for that word. So the word the, let's assume that the word the appears in every document in the corpus. Well, really every document except one, so that I can do some easy math here. So when I'm looking at this entry, I'm going to compute log of the number of documents in the corpus, and let's assume that we have 64 documents in this corpus, and then we have 1 plus, and I assume that the word the didn't appear in one of these 64 documents, must have been a pretty short document. And so what this gives us is the 0 that we talked about before. So the gets downweighted completely by 0. In contrast, when we look at messy, let's assume that, again, we have some 64 total documents, and let's assume that the word messy appears only in 3 of these documents. So we get log of 16, which if we use log base 2, gives us 4. Okay, so this is our term frequency and our inverse document frequency for these 2 words. And when we go to compute the term frequency, inverse document frequency for this specific document, which is going to be our new representation of this document, we simply multiply these 2 vectors together. So there's some numbers here where the word the turns into a 0, and then these are some other numbers, and then the word messy is going to be upweighted to a weight of 20. And again, there's some other computation we're doing for all the other words in our vocabulary. But the point that we want to make here is the fact that these very common words like the get downweighted, and the rare and potentially very important words like messy are getting upweighted. Okay, so we've talked about how to represent documents, and we've also talked about how to measure similarity between documents. So now let's turn to the actual task of interest, which is retrieving a document. So somebody's reading an article, we're assuming they like that article, and we like to present them with another article to read. So in particular, one of the most popular ways of doing this is something called nearest neighbor search, where we have our query article. That's the article that we're reading. And then there's the corpus. That's all the documents out there that we want to search over to recommend some new article. And so what we need to do for nearest neighbor search is we need to specify a distance metric. So this is going to be like our measure of similarity that we talked about earlier. And then what this algorithm is going to output is a collection of related articles. One example of nearest neighbor search is just something called one nearest neighbor, where you have your query article and what you're going to return is just simply the most related article out of all those articles out there to the query article. And the algorithm is very straightforward. We're just going to search over every article in our corpus. These are all these little green articles. And we're going to compute the similarity using the methods that we described earlier between the query article and this article we're examining in the corpus. And then if that similarity is better than the best similarity that we've found so far, then we're going to keep this article as our best article that we found so far. And then at the end, after we've iterated through every article in our corpus, we're going to look at what was the best article that we found, and we're going to recommend this to the reader. A very straightforward variant of this is something called k-nearest neighbor search, where instead of just outputting the most relevant article that we found, we're going to present the reader with a collection of k different articles that are the top k most relevant articles. And the way that we do this, the algorithm is nearly identical, except instead of keeping just the most related article, we're going to keep a priority queue of the top k articles found so far. Okay, so that's one way to retrieve a document of interest. Just take all articles out there, scan over them, and find the one that's most similar according to the metric that we define. But another thing we might be interested in doing is clustering documents that are related. So for example, you might have a whole bunch of articles about sports or world news or different things like this. And if we can structure our corpus in this way, if a person is reading an article that's about sports, then we can very quickly search over all the other articles about sports instead of looking at every article that's out there in the entire corpus. But a challenge here is the fact that these articles aren't going to have labels. It's not going to be like the New York Times where you go and somebody says, this is an education article. Okay, all we have are articles, and what we like to do are discover these underlying groups of articles. Okay, so the goal is to discover these groups or clusters of related articles, and like I mentioned, one might represent a set of articles like sports, and another one a set of articles about world news. For the time being, let's actually assume that someone provides us with labels. So somebody goes through and reads every article, or at least a large subset of articles in our corpus, and labels them and says, okay, these articles, these are all about sports. And these ones, these are about world news, and these about entertainment, and these ones are about science. So we have some set of articles that have labels associated with them. Well, in this case, when we have our query article and we'd like to assign it to a cluster, this ends up being just a multi-class classification problem, because the question is just, here's my query article, I don't know the label associated with it, and I have a bunch of labeled documents. I have the labels world news, science, sports, entertainment, technology, and I just want to classify which class this article belongs to. Okay, so this is the question. It's just a multi-class classification problem. So if that were the case, that would be an example of a supervised learning problem. We're going to assume that no labels are provided, and we're going to aim to infer groups of related articles, which are clusters. Here, the input is going to be a vector. So every observation that we're plotting here is our word count vector. And in this case, we're just looking at a very simple example with a vocabulary that only has 2 words. So we have a vector, we have word 1 and word 2. And this axis here is word 2, and this axis is word 1. Of course, remember that in reality, we tend to have very large vocabularies and we have these big high-dimensional vectors. So when we're plotting our observations, they're really in this high-dimensional space. But for visualization, let's just look at this 2D representation. So we have a whole bunch of documents here, all represented by their word counts over these 2 different words in the vocabulary. Okay, so that's the input to a clustering algorithm. And the output is going to be cluster labels. And so what I mean is that this observation and all of these observations here, all of these get labeled as red. So maybe they get applied some cluster label 1. So let's just call this cluster 1. So for every document, it's going to get some label. So that'll be labeled 1. Then all of these observations here, they're going to get some other label. And let's assume that this is cluster 2. So this observation gets the label 2. And all of these observations here would get the label 3. So that's going to be the output of this algorithm. And maybe what you could do is post facto, you could go through and look at some articles in cluster 1, and you could say that this cluster is really a cluster about sports. And I just want to write down explicitly that this label is provided post facto. Okay. Well, this is an example of an unsupervised learning task because we're operating without any labels. All we have are our observations, and we're trying to uncover some structure in these observations. So again, just to reiterate, the input are our word count vectors, and the output is for every document in the corpus, we're going to associate some cluster label with that document. Okay, well, what defines a cluster? Well, every cluster is defined by a cluster center. So maybe I'll mark the cluster centers with X's. And then there's the shape to the cluster. And these ellipses are representing the shapes of each of these clusters. And so when we think about whether this observation, this observation here should be assigned to the green cluster or the red cluster, what we're doing is we're looking at how similar this article is to other articles based on the shape of this cluster. So we score every observation based on the cluster center as well as the shape of that cluster. And in this case, because this cluster has this kind of oblong skewed shape, it actually gets assigned to the green cluster instead of this red cluster. But another approach, which is very common, is instead of looking at the shape of the cluster, we just look at cluster centers. So we just measure the distance of this observation. So maybe let me change colors here. So this alternative approach here is we would just look at the distance of this observation to the green cluster center versus the red cluster center. And in this case, it would be very challenging to decide whether that article should go with the green cluster or the red cluster. But there are other cases like this observation here where it's pretty obvious with this metric that it would get assigned to this red cluster. Well, let's look at an algorithm for doing clustering that uses this metric of just looking at the distance to the cluster center. Okay, so here we see the data that we're going to want to cluster, and this algorithm, which is called the k-means algorithm, starts by assuming that you are going to end up with k clusters. So you specify the number of clusters ahead of time. So the reason the algorithm is called k-means is we have k clusters and we're looking at the means of the clusters, just the cluster centers, when we're assigning points to the different clusters. Okay, so let's talk about how we initialize the algorithm. So the first thing we do is one example, there are many ways to initialize where we put the cluster centers. We will talk about these things more in depth later. But for now, let's just assume that we randomly assign 3 different cluster centers if we're going to assume some 3-means algorithm here. And then the first step is we're going to assign every observation to the closest cluster center. So this observation here gets assigned to the red cluster. These observations are all closest to the green cluster, or this green center here. And these are all closest to the blue center. And a way to do this is something that's called just a Voronoi tessellation. So we look at the cluster centers, and what we can do are define, let me switch again to this magenta cluster color. So here are the cluster centers, and we can just define these regions here. And these regions represent areas where any observation we might get, so any new observation, that's a very bad color on red. What other colors do I have? How about white? Cool. White. So some new observation I get here, if it falls within this red region, I know is closest to this red cluster center. So that's what these colored regions are representing. Okay, so that's the first step of the algorithm. So what I end up with are observations that are assigned to clusters. But I just randomly initialize those cluster centers, so I probably don't believe that that really represents the structure underlying the data. So what I want to do is I want to iterate this process where I then want to update what my definition is of the cluster center based on the observations that I've assigned. So if you remember this red cluster here, it just had one observation assigned to it. So when I go to revise the cluster center for that cluster, it just moves to the previous observation. But for this green cluster, if I look at the previous cluster center here, well, I'm going to move it to the center of mass of all these observations that have been assigned to the green cluster, and the center of mass of all of them is here. So this becomes the new cluster center. And likewise, I do this for all of the blue observations. This is the new cluster center for this blue observation. Okay, so now I have a new set of cluster centers, and what I can do is redraw this Voronoi tessellation and reassign my observations to the nearest cluster center, and then I iterate this process until convergence. Okay, well, we've talked quite exhaustively about this notion of clustering for the sake of doing document retrieval, but there are lots and lots of other examples where clustering is useful, and I want to take some time just to describe a few of them. So one application is for image search. So imagine you're going and you're searching for you go on Google image search and you type in the word ocean. Well, it would be really helpful if we could structure all the images we have by some set of categories like ocean, pink flower, dog, sunset, clouds. So clustering is very helpful for doing structured search. Another very different application is maybe we want to group patients by their medical condition. So here a goal might be to better characterize subpopulations as well as different diseases. So as an example, we can look at a whole bunch of patients that have seizures. So these 3 brains represent 3 different patients, and they have different recording setups that are measuring their seizure activity. And so for each of these patients, we get a collection of recordings of different seizures that they exhibit over time. So each one of these colored squares represents a different recording of a seizure. And between these different patients, there might be similar types of seizures that appear in these different patients. And so what we can do is we can take all of these seizure recordings from these 3 different patients and think about clustering them. And if we identify different types of seizures in this way, this can allow us to better treat the types of patients that we're observing based on understanding what types of seizures they exhibit. Well, another application is thinking about doing product recommendation on Amazon. So, for example, on Amazon, there are a lot of third parties that come and they post some product to be sold, and they provide a label of what that product is. So, for example, maybe a person wants to sell a crib, and they label the crib fairly reasonably as being a furniture item. So maybe it would get posted under the furniture category. But if instead we look at who purchases this item, and we look at their purchase history, and we look at other people with similar purchase histories, so maybe the person who purchased this item also purchased a baby car seat, well then maybe what we can do is we can infer that a better label for this crib, which had been labeled furniture, is really to have labeled it as a baby product. So in addition to discovering groups of products that are related, that have, based on purchase histories of these items, we can also use that to discover groups of related users on Amazon, and that can be used for targeting products to those users. And finally, we can think about structuring web search results. So for example, search terms can have multiple meanings, like the word cardinal. If I type this in to Google, maybe I mean I want an article about a cardinal the bird, maybe about the baseball team, or about a cardinal, a religious figure. So if we can structure our articles based on their content, using the same types of ideas we've talked about in this module, then I can improve my search results that I provide to people. And the list of applications goes on and on. Another one that's quite interesting is thinking about collections of neighborhoods. And there are a few applications where you want to discover similar neighborhoods. One is if we want to estimate the price of a house at a very small local regional level. So in this case, a challenge is the fact that we only have a few, or very often, no house sales observations within a very small neighborhood. So if we want to estimate the value of the house in that neighborhood at a point in time, it's very hard to do that because we have no other houses to base our estimate off of in that neighborhood. However, if we can discover other neighborhoods that have similar types of house price dynamics, then we can come up with a good estimate of the house in the neighborhood with few or no sales by leveraging information that was discovered from this other neighborhood that was discovered to be related to the current neighborhood. So the idea is to discover clusters of neighborhoods, and then within those clusters we can share information like these house sales informations to form better estimates. So this is the solution that I'm describing here, is to cluster regions with similar trends and then share information within a cluster. And the same idea of discovering related regions can be used for helping to forecast violent crimes to better task police forces to different regions. So again, once we discover different neighborhoods that have very similar crime dynamics, we can form better predictions of the rates of violent crimes in those neighborhoods, and then use that information to task police to those regions. In this module, we've talked about a document retrieval task, and we've also talked about a notion of clustering, where we're trying to uncover some underlying structure in the data. And we've talked about many different areas in which this notion of clustering can be really useful. So let's go through the workflow for a clustering algorithm. And if you feel like you already know this at this point, because you've seen this workflow now in 2 other modules, well, wake up, because this one's going to be a bit different. Okay, so let's talk about our training data. Here, our training data for a document clustering task is going to be a document ID and document text table. So we have a whole bunch of documents and we have all the text associated with each of those. And then we're going to extract some set of features. And we talked about a lot of different ways to represent a document. But the one that I'll use just as an example here is our TF, IDF, term frequency, inverse document frequency representation. And then what we're going to do is we're going to try and cluster our documents based on this representation. So we're going to put these features through some machine learning model, which in this case is a clustering model. And we're going to output for each document a cluster label. So the output white hat is our cluster label. Okay, so here's where things get interesting. Because we want to assess the accuracy of our cluster labels. Well, in this case, we don't have true cluster labels. So I should say this is our predicted or estimated cluster label. But we don't have a true cluster label to compare against. So this Y here, it does not exist. And that's because, as we talked about, we're in an unsupervised learning setting. Unsupervised. Okay, so we don't have that, but somehow we want to assess some measure of accuracy of our clustering. So let's draw a little picture here, which is going to be our Voronoi tessellation in our k-means algorithm, where we have some set of cluster centers, and we have data. Let's just say our data look like this. I don't know, I'm just going to draw some points here. And the measure of accuracy that we're going to use, the way we're going to measure our quality, is to look at how coherent our clustering is. So we're going to look at the distances from each observation to their assigned cluster center. And a good clustering algorithm has those distances very small. Okay, so the goal is to minimize these distances. And so what we see is to measure this accuracy, to measure these distances, what we need is our data, we need our TF-IDF vectors. So those are going to come in here. And then we also need the cluster centers. And so W hat, that's our current estimate of, that's our model parameter here in the k-means algorithm. It's our cluster, let's see if we can spell that correctly, cluster centers. That's what W hat represents. And so of course to measure these distances, we also need W hat. So instead of having actual cluster labels to assess accuracy, we're going to take our document representations and our cluster centers, plug it into this quality measure, which is looking at distances to cluster centers. That's our measure of error, though it's not really an error, it's just a measure of, just a measure of quality. So I won't put that word there because I think that's a little confusing. But let's just write distances to cluster centers. And then what's our algorithm we're talking about? We're talking about k-means as a method of doing clustering. Of course, there are others, but let's focus on k-means. Well, what's k-means doing? Let's just redraw this diagram. Actually, I can just switch to another color. That will save us some time here. Well, k-means is trying to minimize this distance or the sum of these distances. And the way it's doing that is iteratively, it's updating. So this was our W hat that we had before, and we're moving it to a new W hat that represents the center of mass of these points. So these points are getting shifted, and this point will go directly on top of that observation. And so this is the workflow of clustering. Let's just say it at a high level one more time. We take our documents, we represent them in some way using either raw word counts, TF-IDF, normalizations of these things, lots of different bigrams, trigrams, things we can look at for our document representation. Then our clustering algorithm, like k-means, is producing cluster labels, and iteratively we're looping through here again and again, updating our cluster centers, that's the parameters of these, this clustering model, by looking at how far our assigned observations are to those cluster centers. Okay, so in this module, in contrast to some of the other modules, we actually presented you with some of the algorithmic details behind the methods that we're looking at. Specifically for clustering, we talked about the k-means algorithm. And then for our document retrieval task, we also talked about doing nearest neighbor search and provided some of the algorithmic details for that. And you specifically explored that in an IPython notebook for doing Wikipedia entry retrieval. So at this point, you really should be able to go out there and build a really cool retrieval system for doing news article retrieval or any other really cool retrieval that I can't think of right now. But of course, there's lots of interesting examples. So go out there and think of the ideas I can't think of right now.
In this module, Emily covered various techniques for retrieving documents, exploring representations for our data like word counts and TF-IDF. Now we're going to build a really cool notebook where we put these ideas together and build a document retrieval system using TF-IDF. So let's go ahead and do just that. As usual, we're going to be using a Python notebook, and in this one, I'm going to change the title to Document Retrieval. And here we go. And again, as usual, I'm going to hide the header and hide the toolbar to give us a little bit more space. Okay, let's go ahead and fire up GraphLab Create. So we're going to do import GraphLab, since we're going to be using it again in our notebook. Now the first step, we're going to load some data. So let's load some text data. And this is interesting text data from Wikipedia. And it's pages on people. So cool data set. I'm just going to load it. And so we're going to say people, which is going to be an S-frame, is going to be graphlab.sframe from a file, and the file is called peoplewiki. Right here. And here we go. We're loading it. And the first thing that I'm going to do is just look at the few top lines of that file. So I'm just going to call head, and you should see what we have. So this URI is basically the location of that page on Wikipedia. This is the name of the person involved, and the text of that page about that person. And you have this for a pretty nice number of people here. So if you type len of people in our data set and type enter, you see that we're talking about 59,000 people in this data set. It's a pretty good set, and you'll see with TF-IDF we're going to do some really interesting document retrieval, even in this relatively large data set. So the first thing that we're going to do is just explore our data. So let's explore the data set and check out the text it contains. So let's start looking at a particular person data set, and we're going to look at the page for Barack Obama, who is the current US president. So out of this people S-frame, I'm going to select the one whose name, so that's the name column, is equal to Barack Obama. And so I pressed enter and I created this new variable called Obama. And if you take a quick look at it, you see that it has the URL for the Obama page, the name Barack Obama, and the text for that page. So let's dig in and see what that text looks like. So for Barack Obama, you'll see that Barack Hussein Obama was born on August 4th, 1961, and is the 44th and current president of the United States. So pretty natural text, what we'd expect for this kind of data. So we can also look at some other personal data set. So for example, there's an actor called George Clooney, so who's been in a lot of movies. So if you look at the people S-frame, we're going to select, so this is again a filter operation which we've been doing almost every notebook now, whose name is George Clooney. And then I'm just going to go ahead and show you the text that we get for George Clooney. And you see that George Timothy Clooney was born in 1961. So basically he's the same age as Barack Obama, but he's not president. He's an American actor, writer, producer, director, and activist right here. Cool. So this is the data we're working with. It's a pretty neat data set. And let's explore it a little bit more. So in the lectures, Emily talked about building word counts and some of the challenges with word counts. So let's start by taking a quick look at our word counts. So for example, let's get the word counts for the Obama article. So we had an article on Wikipedia about Barack Obama, and what we're going to do first is just take a quick look at the word counts for that article. So I'm going to take this Obama variable that we created, and I'm going to add a new column to it called word count. So this is going to store the word count for Barack Obama, and we can do that by just calling, you could write, as we showed in the classification sentiment analysis notebook, you could write a function yourself to compute the word counts, but we just have one ready for us in the text analytics toolbox. So we're just going to use it to get started quickly. So we just call count words. See, there's count n-grams. We're just going to count words, which is the unigrams, single words. And as input, we're going to give it the Obama text. So I've now done it, and let's take a quick look. Let's just print the Obama word count. And here we go. We've now printed the Obama word count. And you see that operations appeared with once, represent appears 1, office appears 2, unemployed appears 1, and so on for various words. And it's not super intuitive here. So we're going to play with this a little bit. And in the process, I'm going to show you a cute little data engineering trick that might be useful in other areas. So let's, what we're going to do next is sort the word counts for the Obama article. Now here's something to understand a little bit better. If you notice, the word count is really a dictionary. This is the kind of the Python dictionary. You're given a key, and in this case is the word. For example, Honolulu, where he was born, weather, marriage, and so on. And then it has a value of 1, 2, 3, 5, 30, which is the count, how often that word appeared. And so what we're going to do is sort this. And to sort those words, we have to turn it into a table where one column is the word, the key of the dictionary, and in the second column is the count. And then we're going to sort that table. So the way to do this, there's various ways to do it in Python, but let me show you a quick little trick that you'll find useful. So I'm going to create a new table called the Obama word count table. And what we're going to do is take this Obama, and I'm just going to select here, out of all the columns in the Obama table, I'm just going to select the word count because this will make the printing a little neater. But you could have done with the whole table too. And then I'll call a function called stack. And this function stack is extremely useful. It takes one column of an S-frame that contains a dictionary and stacks it one on top of each other into multiple columns. In this case, two columns, one for word and the other one for count. So we're going to stack a particular column called word count, the one that we really care about, and generate some new columns. So we have to call them, give them a name. So new column name. In this case, there are two of them. One I'm going to call word, and another one I'm just going to call count. And if I execute this, and we take a look at this table, Obama word count table dot head, just the first few lines, you'll see it shows words normalize, sort, combat, but it's not sorted. It's not a sorted table. So what we're going to do next is just take this table and just sort it by the count. And we've seen this before, but it's kind of pretty simple. So I'm going to take the Obama count table, and I'm going to call the sort function, and I'm going to sort it by the count column, sort by count, and I'm going to say ascending equals false. So instead of sorting in an ascending order, 1, 2, 3, like we normally sort, we're going to sort in a descending order, 3, 2, 1. So if I press enter, you'll see the most common word is the, followed by in, followed by and, off, to, his, eventually Obama. And so act, a, he. So these are not that informative. And in the lectures, when we were working with Emily on them, she covered the issue that these uninformative words can drown out the important words. And that's why we introduced the notion of TF-IDF. And so let's actually compute TF-IDFs. Now, I can't just compute TF-IDF, and this is an important note, by the way. I can't just compute TF-IDF for the Obama article in isolation, because TF-IDF depends on the entire corpus. You need that normalizer, which is the number of times a word appears in every article. So I have to show it, I have to compute it for the entire corpus. So let's go ahead and do just that. So here we go. So I'm going to compute TF-IDF for the corpus. And I'm going to do this in two steps. First, I'm going to compute the word counts for the entire corpus. So I'm going to add a new column to the people table called word count. Remember, we just did this only for Barack Obama. So now we're going to do it for everyone. So I'm going to call graphlab.textanalytics.count words, and I'm going to put in the input, which is going to be the text column. In other words, I'm going to count the words in the text column. And just so that we're clear, let me just print the S-frame people after we do this. So I'm going to print the first few lines of that S-frame. So here we are, we've executed. Now we have the URI column, the location, the web page, the name of person, text, and now we have this dictionary of word counts on the right. It's a new column. Good. So next, we're going to compute the TF-IDFs. So just like with word counts, you could have implemented your own TF-IDF system. That'll take you a little while to do. So GraphLab Create has one already implemented, and we're going to just use that to make this whole process pretty quick. So we're going to call graphlab.textAnalytics. Just like with word counts, there's a function here called TF-IDF, and all you need to do is give an input, just like we're going to give the input the word counts, and it will output the TF-IDF. And let me just again show you what that looks like. Oops, I did a little typo here. That should be word count. That's what I call the column, now word counts. And now I'm going through the whole corpus, the 15,000 documents, computing the frequency of words, normalizing, and what we end up with is a table where for every document, it calls the table docs, it has a dictionary of TF-IDFs for each one of those documents. And just so that we get all this right, I'm going to add a new column to the people table, and this new column is going to be called TF-IDF, and I'm just going to store in there the TF-IDFs that I just computed. So it's all in one table, and it's the doc column, docs column. Here we go, we just added it in. So now we have TF-IDFs for every document computed and stored in there. Let's do some examination. So here's what we're going to do. We're going to examine the TF-IDF for the Obama article. So just like we examined and sorted the word counts, now we're going to examine and sort the TF-IDFs. I'm going to reread the variable for Obama because we now added these two new columns and I want a latest version of it. So I'm going to take people, and I'm going to select out of the people the one whose name is equal to Barack Obama. Okay, I've done it. I've created this Obama. And now, just like we did with word counts, I'm going to create an Obama TF-IDF table so that we can sort it. It's a dictionary. We're going to just sort it exactly the same way as we did before. We're going to stack it and then sort it. And I'm going to do this. Actually, instead of creating a table, I'm just going to do it in one line. Oops. I'm going to do it just in one line here. So I'm going to write out what we did earlier. So I'm going to just take the Obama variable, and I'm going to select only the TF-IDF column, so it looks a little prettier. Then I'm going to call the stack method, which takes a dictionary and just stacks it into two columns. So I'm going to stack TF-IDF, and I'm going to output new column names, and those names are going to be the word and the TF-IDF. And let me show you something. Oops, I forgot to close. Okay, here. And let me show you a little neat trick that you can use with Python in various ways. I'm just going to chain the sort command at the end of this. So I'm just going to type .sort, and I'm going to sort this output on the TF-IDF column, and I'm going to say ascending is equal to false. So what I did in multiple lines before, now I'm doing in just one line. I'm taking the Obama column, TF-IDF, I'm going to stack it into a word column, a TF-IDF column, and then I'm going to sort it in a descending order. So from highest to lowest. And if you remember, just before we run this, when we did it for just word counts, it looked like this. There was the most popular word, then in, then on, then off, and to, his, then Obama, act, a, and he. So those words are mostly uninformative except for the word Obama. So let's execute it for TF-IDF. And what we see here, voila, the most informative word is Obama, which makes a lot of sense because the article is about him. But then you have act, Iraq, control, law, order, military involvement, response, democratic is from the Democratic Party. So you see lots of action going on here around words that are important with respect to Obama. So let's take these TF-IDFs and do a couple of fun things with them. So first, we're going to manually, so let's, okay, so let me just type in here. So we're going to manually compute distances between a few people. So the goal here is just to show what those distances look like, just to get a sense of what we're learning from TF-IDF. So for example, let's take 3 people. So we already talked about Obama. We already have that Obama variable in there. Let's create 2 new variables. Let's take Clinton, which out of the people, I'm going to select the person whose name is equal to Bill Clinton, the former US president. And let's select another person. So for example, let's select Beckham. So Beckham is a famous British English footballer. And so we're going to select out of the people the person whose name is equal to, his name is actually David Beckham. Now that we selected Clinton and Beckham, let's compute the similarity between those 2 people and the President Barack Obama. So what we're going to do is ask the question, is Obama closer to Clinton than to Beckham? Okay, a little mistake here. So is Obama closer to Clinton than to Beckham? Now, there are various ways to measure similarity or distances between 2 vectors, or in this case 2 documents. We computed the TF-IDFs, and what we're going to do is compute the distance between this different documents, the one about Clinton, the one about Obama, and so on. So I'm going to use distance metrics that are already implemented inside the GraphLab Create, so we don't have to implement them ourselves. So if you look at GraphLab.distances and press tab, you'll see several options here. The Euclidean distance that we talked about in class, cosine distance, Jacquard similarity, and so on, that we're going to see throughout this specialization. We're going to use cosine distance. And just as a little note, normally we think about cosine similarity, if you've heard of it, where the higher the number, the more similar 2 articles are. Here we have a distance version of this number, so the lower the better. The lower the cosine distance, the closer the articles are. So the question is, what is the cosine distance between Obama's TF-IDF and that of Clinton? But notice that I have to select the column TF-IDF, and I have to add a little 0 at the end here because it is the 0th row of this table. The table only has 1 element in it, but we still have to say what row of the table we're looking at. And so we're going to compare the Obama TF-IDF with the Clinton TF-IDF, also at 0, in terms of the cosine distance. And you see that distance is 0.83. Now the question is, what is the distance between in the same metric in the cosine distance between Obama and Beckham. So I'm going to type Obama TF IDF computed at 0 with Beckham's TF IDF also at 0. And you'll see that this distance is 0.97. The biggest distance you can get is 1, in fact. And so in this case, Obama is much closer to Clinton than he is to Beckham, which makes a lot of sense. But we've done this just manually for a few people. How do we automate this process of finding out how close an article is to other articles? And in this case, how close is a person to other people? In the lectures, Emily talked about nearest neighbor models and how they can be used for document retrieval. So today, we're going to actually do some cool document retrievals using a simple nearest neighbor model. In the lectures, Emily talked about nearest neighbor models and how they can be used for document retrieval. So today, we're going to actually do some cool document retrievals using a simple nearest neighbor model. So next, we're going to build a nearest neighbor model for document retrieval. And here we go. Nearest neighbor model for document retrieval. Again, you could implement your own, but we have one already implemented here that we can use, which is great for this first course. So we're going to use the one from GraphLab, and it is called nearest neighbors. So here, nearest neighbors. And just like the other models, you use the verb create to create a nearest neighbor model. And so we're going to give it as input the people table. And we have to say what features we're going to use in the nearest neighbors. So the features are going to be the TF IDF, just like we've been using for the cosine distances above. And I'm going to provide a label column, and this label column is going to be the name. So when I return my nearest neighbors, it's going to return the actual label of the nearest neighbor, so the name of the person, and that will make the printouts prettier. So that's good. It's there for us. So it should only take a few seconds, and we will have, there we are, have a nearest neighbor model for document retrieval. So now we can use it. So let's go ahead and use it. So I'm going to just create another header here and say applying the nearest neighbor model for retrieval. And let's see what we get. So the first question is, so let's do our first query. So who is closest to Obama? So who are the closest people to Obama in the data set? So if you just take our k-nearest neighbor model, we can use the method query, the function query associated with it, which just queries the model with some input, so in this case Obama as our input, and gives me back the nearest neighbors. So who are the nearest neighbors to Obama? We'll compute it, and it takes, it's very quick, and I'll say, okay, the closest person to Obama is Obama himself, which makes sense. But after that, we have Joe Biden, who is the current US vice president. So the president is closest to the vice president. And then we find a few other politicians, including former President Bill Clinton, which we saw above.
Okay, so in this module, we're going to talk about recommender systems. And one prototypical example of where recommender systems are really useful is in recommending products. So imagine you have a large set of products and there are some users and you want to recommend a subset of your products to those users. Well, the question is, how are we going to do this? And what we're going to talk about is how to use machine learning techniques in order to use the past history of your own purchases as well as the purchases of other people to determine which products to recommend to you. And recommender systems just have a really, really wide range of applications, and they've exploded in popularity over the last decade. But Amazon was an early pioneer in this area, focused on the application we're going to be talking about, which is product recommendation. But another example that really popularized recommender systems was a competition that Netflix ran starting back in 2006, ending in 2009, where there was a $1 million prize for the person who provided the best recommender system for recommending movies to users. And we'll talk a little bit about that application in this module. But it really spurred a lot of activity in this area, developing new recommender systems and a lot of research following that. Let's start by discussing some areas in which recommender systems are playing a really active role behind the scenes. And as we're going to see in this discussion, depending on the specific application, different aspects of the objective we're trying to optimize are going to be important. But before we start talking about recommender systems, it's really important to talk about the idea of personalization, because personalization is transforming our experience of the world. As we talked about in the clustering and similarity module, there are lots and lots of articles out there and lots of web pages, and we can't possibly be expected to browse all of them. So another example here is YouTube. So YouTube, it's quoted that there are roughly 100 hours of video recorded per minute. And the question is, what do I care about? I go on YouTube and I want to watch some video that's of interest to me. So this is an example, clearly, of information overload. There's just way too much content there for me possibly to be able to go and for me to find what I'm interested in without somebody helping that content come to me. So browsing, the traditional form of browsing, is history. There needs to be some way in which the content that's relevant to me is automatically discovered. And so this is the notion of personalization, where we want to connect users like myself who goes to YouTube, and items, which in this case are going to be videos on YouTube, need to somehow be connected. Okay, so personalization is going to play a key role in this notion of recommender systems, and now let's talk about some examples where recommender systems are very important. So one very classic example that we mentioned a little bit earlier was this idea of Netflix, where here people go and they watch videos, and Netflix has this goal of trying to make suggestions of which movies or TV shows might be of interest to the person who's come to this site. And the question is, how are we going to go about doing these recommendations? Another example, again going back to something we talked about earlier, is Amazon making product recommendations. So you go onto Amazon, you purchase some product, and you'll see on the site that it makes a recommendation of other products you might be interested in. But one important thing to incorporate in these recommendations is the fact that not only do you have to take into account the interest that the person had in this one session. So for example, here we're showing that somebody bought a book about websites and might be interested in another book about web applications. Or for example, my most recent purchase on Amazon were shoes for my son, but the interest that I have in making that purchase of shoes isn't my only interest. I'm not only looking for shoes for a 1-year-old. There are lots of other reasons why I go to Amazon and make purchases. And if you look at my history of purchases, you're going to be able to make much better recommendations for me than just based on a single session. And likewise, recommendations might change over time. So there's interest in making recommendations, for example, what I might be interested in purchasing today. So if you look at my purchase history, a year ago, I was buying a lot of newborn products, so newborn baby products. But that's probably not something that I'm very likely to purchase today. So the recommendations that Amazon presents to me today have to adapt with time. So just as on-demand video with personalized recommendation has really revolutionized how people watch movies and TV shows, well, likewise, there are a lot of websites that provide streaming audio with personal recommendations. However, in this case, unlike thinking about on-demand video, here we want one song to play after another. And what we want is we want some coherent stream of songs. So songs I've liked, I want to play similar songs. I don't want to rapidly switch between, for example, playing some cafe indie, song to all of a sudden playing a heavy metal song. But at the same time, I don't want a song I just heard to play again and again and again. So I want some sense of recommendations that are coherent, but I also want them to provide a diverse sequence of songs for me to listen to. Okay, well, another critical area where recommender systems have played a very active role is in social networking. So for example, on Facebook, there are tons and tons of users, and we want to form connections between these users. So for example, here might be a graph of connections between users on Facebook, and maybe I'm this pink node right here, and Facebook wants to recommend other people I might be interested in connecting with. In this application, it's important to note that both the users and the quote-unquote items are of the same type. We're both people. So when I'm a user on Facebook, the things that are being recommended to me, the items, they're other people. So we're going to end up with users and items being of exactly the same type in this application. But the recommendation systems that we've talked about have really focused on online media. But more and more people are realizing other areas in which recommender systems can play a really important role. And just as one example, we can think about what's called drug-target interactions. And here, maybe we have some drug that's been studied, for example, let's talk about aspirin. It's been well studied as a treatment for headaches. But what if it's discovered to have some other possible use? So, for example, for blood thinning for heart patients. If we can find these types of relationships, if we can repurpose this drug for some other treatment, then that can be really useful because it's really quite a costly and lengthy process to get FDA approval for a completely new drug. But if we can take a drug where the types of side effects and the possible risks associated are already well known and well studied, then it's a lot easier to get approval for treatment with some other condition. So this is a case where we might say, if you like aspirin for headaches, you might also like aspirin for your heart condition. So recommender systems are playing an active role in medicine as just an example of the diversity of applications where we see these types of systems. We talked about a lot of application domains where we see recommender systems, but now let's talk about how we actually build a recommender system. And there are lots and lots of approaches for performing these types of recommendations, and let's discuss some of them. And the first, level 0 way we might think about recommending products is just based off of the popularity of each product. And this approach is actually really popular on things like news sites. So for example, New York Times has this list on the side of the website that says the most popular articles, and it's sorted by different topics. For example, the most emailed articles. So here, when we think about recommending articles to other readers, we're just sorting the articles by how often they were shared by other readers on New York Times. So this can work fairly well. I might actually discover an article that I'm interested in using this type of approach. But one disappointing thing about it is it completely lacks personalization because all the recommendations are based off of the entire population of New York Times readers out there, which is actually pretty diverse. So instead, I would of course love to have a method that knew a little bit more about me and my interests to recommend news articles to me. So let's try and add in a little bit of personalization using a classification model where we're going to use features of both the products and the users to make our recommendations. And this classification model is going to look exactly like the classification model that you're just learning from Carlos, where there you guys were using classification to do sentiment analysis. But here we're going to use this model to classify whether a person likes or does not like a product. Okay, so this classification model is going to take in features about the user, features about the past purchases of that user, features about the product that we're thinking about possibly recommending, as well as potentially lots of other features that we can talk about. And we're going to shove all these features into our classification model, and it's either going to spit out, yes, I believe this person's going to like this product, or no, I don't think they're going to like it. Well, this type of classification approach has a lot of things going for it. So first, it can be very personalized. We're using features of the user as well as the user's purchase history. And in addition, this model can capture context. So for example, we can take into consideration the time of the day, what that person just saw. So for example, maybe I'm much more likely to purchase a textbook during the day or home products at night. And one other really nice thing about this approach is the fact that it can handle a very limited user history. So for example, let's say I'm a user on Amazon and I haven't purchased many items in the past. So for a lot of approaches, there might be a lot of ambiguity about what I might be interested in or not. But if you have information about me, such as my age, that alone can be very predictive of what I might like or not like. But this approach has limitations as well. And one of the important limitations is the fact that these features that we're talking about that can be so informative about the products that we're going to potentially like or not might not be available. So for example, you might not know my age, you might not know my gender, and the list goes on and on. And likewise for a product, you might also have either missing information or very poorly written product descriptions, especially on Amazon where you have lots of people on there selling different products. The quality of that information might be pretty low. So often what we actually see is something that's called collaborative filtering, which we're going to talk about next, can actually work better than this type of classification approach. So this notion of collaborative filtering is that somehow we want to leverage what other people have purchased in the case of product recommendation, or other links more generically between users and items to make recommendations for other users. And so it seems very intuitive that when we're thinking about doing product recommendation, that we want to build in information like if a person bought this item, then they're probably also interested in some other item because we've seen lots and lots of examples in the past of people buying those pairs of items together. Maybe not simultaneously at the same time, but in the course of their purchase histories. Okay, so this brings us to the idea of co-occurrence of purchases. So for example, if I was just on Amazon buying diapers, well, we've probably seen lots of examples of people who bought diapers also bought baby wipes. Okay, so how can we use this type of co-occurrence of purchases to make recommendations? Okay, so let's talk about this co-occurrence matrix that we're going to build up. And this is going to store all of our information about which purchases people bought together. And again, when I say together, I don't mean simultaneously, just together at some point in their history of purchases. So I'm going to build up this matrix C. And this matrix is an items by items matrix. Okay, so we're going to list all the different items for our rows of this matrix, and likewise all the different items for the columns. So for example, maybe this row of this matrix might be the row corresponding to diapers, and then if this is, let's say, the third row of this matrix, then I would also have that the third column of this matrix corresponds to diapers as well. Okay, and so if I want to say that many people purchase diapers and baby wipes, let's look at the row for diapers, and then we scroll over to the column for, let's say this column here is for baby wipes. And in this entry of this matrix, there's some number entered, and that number represents the number of people purchasing both diapers and baby wipes. Okay, well, let me ask you a question. Is the number of people who purchased diapers and baby wipes the same as the number of people who purchased baby wipes and diapers? Yes. So we would go to the baby wipes row and this diapers column, and notice that this is the exactly same number. Okay? And so what this means is this is a symmetric matrix that if we look across the diagonal here, then we're going to see a reflection. If we took this matrix and folded it across that little diagonal line I just drew, you would get exactly the same numbers matching up. Okay, and just to reiterate, the way we're going to build up this co-occurrence matrix is we're going to search through all the users' histories of purchases they've made and count. And every time we see a purchase of diapers, we'll add of diapers along with all the other items. We're going to add one to that entry, and we're going to keep incrementing that matrix as we're searching over users. Okay, but now let's talk about how we're going to use this co-occurrence matrix in order to make recommendations. And it's really, really straightforward. So let's say that a user has just purchased diapers and I want to make some recommendation for them. Well, what I'm going to do is I'm going to look at the diapers row of this matrix. So if we go back to that C matrix here, I'm going to grab out this diapers row and I'm just going to draw that row here. And what this row has is how often people bought diapers, and remember, baby wipes was one of the items. Oops, sorry, not baby items, baby wipes. And that has, let's say, 100 counts. And then there's also, let's say, pacifiers. And maybe there are 4 counts of pacifiers. Let's think of something else. So let's say that there's some DVD. Let's say there's no counts of those DVDs. We're going to have this whole vector of counts of how many times people who bought diapers bought all these other products. Okay, well, using this, now we can very straightforwardly make our recommendations. All we do is we sort this vector and recommend the items with the largest counts. So maybe we'll recommend baby wipes and milk and baby food and things like this for somebody who just purchased diapers. One issue, though, that we have with these co-occurrence matrices is the fact that they have to be normalized. Because let's talk about what happens if we have a very popular item. So one of the most popular items for babies is diapers. There are lots of these around here. They're very, very useful when you have a baby. So basically, if you're going to purchase any baby item on Amazon, you're also very likely at some point to have purchased diapers. But then let's look at some other item. This is Sophie the giraffe. It's actually one of the most gifted items on Amazon for babies, but it's a little teether. Little babies like to bite on this. It's rubbery, it squeaks, keeps them very interested. But let's think about what happens when we're looking at this other item. So we just purchased Sophie the giraffe, and we want to make recommendations for this person who just purchased this little toy here. So what I'm going to look at is I'm going to look at the counts vector for Sophie. This is for Sophie the giraffe. And again, we have that DVD that nobody's purchasing. Then we have diapers. Then we have baby wipes and all the other products you can imagine. And diapers is some enormous number. Let's say 1 million. Maybe that's not so enormous, but 1 million, it sounds pretty big, or it used to sound pretty big. So what ends up happening is that regardless of what product I'm looking at, regardless of whether I just purchased Sophie the giraffe, or if I just purchased this little stacking toy, or if I just purchased this really cute alligator that makes this sound and it rattles, no matter what I just purchased, according to the process that we just described, I'm really, really likely to recommend diapers to you. So let's think about how to make the recommendations a little bit more personalized and have the effect that everybody buying diapers doesn't mean that that's what I'm particularly interested in when I just bought Sophie. So let's talk about how to handle this. And the way, so this is just to reiterate what I was saying, which is the fact that having these very large counts for popular items drowns out all the other effects. And so we're just going back to this default thing of recommending based off of popularity, which is what we were trying to address with these different types of recommender systems. Okay, so to handle this situation of having very popular items, we can think about normalizing the co-occurrence matrix. And one way in which we can normalize this matrix is with something called Jacquard similarity. So I want to mention that this notion of normalizing this co-occurrence matrix that we're talking about right now is very similar to what we talked about in that clustering and similarity module when we were talking about TF-IDF, the term frequency inverse document frequency, where there we were looking at documents and we said that really, really common words just swamped out other words that we might have cared about. And so we had this way of using TF-IDF to renormalize our raw word counts that we're using to represent our document. Well, in this case, this is a very similar notion of accounting for a very popular item. And the way it works is pretty intuitive. We're just going to count the number of people who purchased some item I and some item J. So number who purchased I and J. And that's what our matrix had before. So those are our raw counts. We're going to normalize by the number of people who purchased either of these items. So the number who purchased I or J. And so a simple Venn diagram explains this very clearly. Here's the world of people that purchased item I. And here's the world of people who purchased item J. And here in this shaded area are the people who purchased I and J. So what we're going to do is we're taking the counts we had before. This is our numerator, this shaded area, purchased I and J. And we're just normalizing by the total area. So that's, let me switch colors here to make this a little bit more visible. So circling the whole entire world of unique users that purchased items I or J, and that's our denominator. Okay, so that's one way in which we can normalize our co-occurrence matrix, and there are other things we could think about like cosine similarity, and we'll talk about these other metrics more later in the course. But this method has its own limitations. Here, one issue is the fact that only the current page matters. So it only matters that I just bought Sophie the giraffe when we're looking at making recommendations for me. We're not looking at the entire history of things that I purchased to inform these recommendations. So let's talk about a way in which we can modify our approach to account for my history of purchases. Okay, so a really simple approach is just to do a weighted average over the scores I would have placed on the products for each item in my purchase history. So let's go through a concrete example of this. Let's imagine that the only items I ever purchased on Amazon were diapers and milk. Okay, so now I want to make recommendations for me, the user that only purchases diapers and milk. And what I'm going to do is I'm going to go through every item that I might think about recommending, and I'm going to compute the score as follows. So let's say I'm looking at whether I want to recommend the item baby wipes to myself. And in this case, what I'm going to do is I'm going to compute a weighted average over how much I would have recommended baby wipes just based on having purchased diapers before. So that's using exactly the techniques we just talked about. So looking at the row diapers and looking at how many times people also bought baby wipes. But then I'm also going to look at the row for milk and then look at how many times people who bought milk bought baby wipes. And I'm going to average these two results to say how much or how likely it is that I would purchase baby wipes given this purchase history that I have. Okay, and of course we could do other variants. Instead of just this simple weighted average, I could weight more heavily my recent purchase history to account for context and so on. Okay, so then when I want to make the recommendation, I just sort this weighted average score and recommend the products that have the most weight. So very similar to the approaches we talked about before, but now we're combining weights based on my purchase history. Okay, but this method still has some limitations. So for example, it doesn't use context like time of day, at least not directly. It doesn't use features of the user like my age or gender or anything like that, because it's grouping all users together when it's thinking about looking at this co-occurrence matrix. And likewise, it doesn't use features of the products. Okay, so everything's just pooled together without any kind of notion of different properties of these products or users to drive these recommendations. And another big problem that we face here is something called the cold start problem. And this is a really important problem that we face in a lot of different domains, but let's talk about it in this context. So the cold start problem is the fact that, let's say we get a new user or a new product. How do we form recommendations, right? I have no observations ever for that product. So I have no notion of how often it's been purchased along with something else because it's never been purchased. And likewise for a user, I have no information about my past purchases. So in the co-occurrence approaches that we've been talking about so far, there's been no notion of different aspects of me as a user or features of the product that are driving the recommendations made. Instead, we're simply counting co-occurrences of purchases and user histories. So a natural question is whether we can somehow use some aspects of who I am and what a product is to drive the recommendations, just like we talked about in the classification approach. So we have some set of features for the user and the product. But here, we'd like to be able to learn these features from the data, and that'll help us cope with the problems we talked about where we might not have features available. And in addition, we'd like to take into account interactions between users and items, just like we did in the co-occurrence application, or the co-occurrence approach. And so we're going to discuss this in the context of a movie recommendation task because it's very intuitive to talk about this application for the methods that we're going to describe. And in this application, what we have as our data is we have this big table where we have a whole bunch of users that are watching some set of movies and they rate those movies. Okay, so our table looks something like this, where this green user went on, watched 3 different movies, gave them a rating of 3 stars, 5 stars, and 2 stars. And then there was this blue user, watched 2 different movies, and this pink user watched 4 different movies. And we have a very big table of the user movie ratings combinations. However, each user only watches a few of the available movies. So we're going to transform this data table into a really big users by movies matrix of ratings. And the reason it's a really big matrix in general is there tend to be a lot of users and a lot of movies. But at the same time, this matrix is very sparse because there are lots and lots of movies. And even though there are a lot of users, there's only a few movies that any given user has watched. And so if we look at this matrix, that, like I said, is a users by movies matrix, then let's say, for example, this row represents user U, and this column represents movie V. Well, this black square here represents the rating that user U gave to movie V. So this is rating of movie V by user U. So there are a few of these black squares, but there are lots and lots of these white squares. So what a white square represents is a question mark. It's a case where a user has not watched a movie or at least has not provided a rating for that movie. And so I just want to be clear that all the white squares represent unknown ratings. They don't represent ratings of 0. It's not that the user did not like that movie. It's just that we don't know what the user thinks about that movie. Okay, so we're going to say that rating U, V is the rating that user U gave to movie V, and it's known for the black squares. Those are cases where we have the ratings, and it's unknown for the white cells. And our goal here is to fill in all these question marks, all these white cells. And the way we're going to do this is we're going to take all the ratings that the user has provided, so all the black squares for that user. So let me switch colors quickly here. So we would take all of these ratings provided by this user and use these to predict what the rating is for these question marks. Actually, all of these question marks we're going to fill in using that user's history as well as those of all other users. Okay, so we're taking, this is the history of ratings of that user and every other user, and using it to predict how much we think they're going to like this movie that they haven't watched. So let me just be very clear. This is, we're filling in a question mark, and I just really want to reiterate that we're not just using the ratings of this user, but we're using all of these ratings when we're going to make that prediction. And I won't bore you by drawing little magenta boxes around every black cell, but just know that's all the information we're using to fill in this really big sparse matrix. But a question is, how are we going to make these recommendations? How are we going to guess what rating a person would give to a movie that they've never watched? Well, let's imagine for a moment that we have some set of features about each movie and each user. So for example, we know that movie V, which in this case is The Shawshank Redemption, is about some set of different genres like action and romance and drama. And so we have this vector for each of these things, which says it's 0.3 about action, it's 0.01 about romance, it's 1.5 about drama. And we have these set of things, so we know what the movie is about. And likewise, for every user, like this user U, we know which of these different genres that user likes. So for this user, we have a vector that says that for action, this user really, really, really likes action, really does not like romance, kind of likes drama, and so on. And we're going to call this first vector the movie vector, RV. We're going to call this user-specific vector LU. Okay, so let's say we know this. Then what would you do to make a prediction of a rating? Well, one thing that might make sense is to take this movie vector and this user vector and see how much they agree. If they agree a lot, then we'd guess that the person would rate that movie very highly. If they don't agree a lot, then we're going to say that it's probably very likely that they will not like that movie and give it a low rating. So we're going to estimate our rating. That's why we put this hat over it to denote that this is an estimate of how much the user U is going to like some movie V that they've never seen before. And so the way we're going to do this is just like when we're measuring similarity between two documents, we're going to take the two vectors. In that case, that might have been a vector of different topics for the document. In this case, we're talking about a vector of different topics about the movie. And so here, we're going to take these vectors, so 0.3, 0.01, 1.5, and so on, and we're going to multiply it element-wise by this vector. So this is our RV, this is our LU, and what we're going to get out is we're going to get out 0.3 times 2.5 plus 0 plus 1.5 times 0.8, and so on. And let's just say that this ends up being some number like 7.2. Just made that up. But if the user vector really disagreed with what the movie was, so let's choose another color. So this is some other user. Let's call this user LU prime. And let's say their vector said they really don't like action. They love romance. They really hate drama. And so on. Well, here, the score is going to be much lower. So we're going to get 0 plus 3 just for consistency, plus 0.01 times 3.5 plus 1.5 times 0.01 plus all these other numbers that really don't agree with one another. And maybe this would come out to be some small number like 0.8. So the point here is that when the movie vector and the user vector agree a lot, we'll get a much larger number than when they don't. So we're going to estimate a much larger rating than in the case where they disagree. And then when we think about making our recommendations, what are we going to do? Well, we'll just sort over all movies that we've predicted for that user. We'll sort by their predicted rating, and then we'll recommend those with the largest ratings. And I want to highlight one thing here. So if you remember, the rating scale was between 1 and 5, or rather 0 and 5. You could provide no stars if you really hated a movie. But the maximum score was a 5. But note here that one of our predictions is 7.2, which is clearly greater than 5. But with this type of model that we're talking about here, we're not restricted. There's nothing enforcing that we're going to stay within a score of 0 to 5. But we can still use this to make recommendations because we just look at the movies with the largest scores, even though those scores aren't necessarily representative of exactly how many stars a movie would get. Okay, so let's take these ratings that we just were talking about, and instead of talking about them for a specific combination of a movie and a user, let's talk about how we can think about representing our predictions over the entire set of users and movies. And to do this, we're going to need a little bit of linear algebra. So in particular, if we're looking at the score that we're giving to a specific movie V for a user U, so this is rating predicted for user U and movie V. Well, what did we say that was? We said we took the user vector LU and we took the movie vector, RV, and we did this element-wise product and summed over the elements of that product. So I'm going to denote that just with this little notation here. Okay, so these little braces here mean we're going to take the vector LU and the vector RV, do an element-wise product, and sum. Okay, so what that represents is we're taking a row of a big matrix L. So there's a row that has a vector LU. So let me write this a little bit more largely here. So this row LU is the vector that we talked about before with how much that user likes different things like action, romance, and so on. And then we take a movie vector, RV. So again, we'll write it more largely here. So RV is indexed over the same set of genres or topics for the movie and has some set of entries. And in this matrix notation, if you're familiar with matrix multiply, to get the entry, so this is the uth row here and the vth column here, if we multiply these together, we get the uvth entry of this resulting matrix. Okay, so if you're not familiar with this kind of thing, that's okay. We're going to talk about it in a lot more detail in subsequent courses. But for those who are, this representation is a very compact way to take all of the vectors for all of the users. So we're stacking up all of the user vectors and stacking up all of the movie vectors. And through this representation, we end up with an entire matrix, which is just like we were writing before. It's a users by movies matrix. So all of the users that appeared here are appearing here, and all of the movies that appeared as columns here are appearing as columns in this matrix. And each individual entry, again, is a combination of a specific row of this L matrix and a specific column of this matrix R here. So to this point, though, we've assumed that we know all these LU user topic vectors, so we can stack them up into this L matrix, and we know all the movie topic vectors, so we put them all together in that R matrix, and then we multiply the two together to get this big prediction of ratings that every user would give to every movie. But an important thing is the fact that we don't actually have this information. We don't have these features about the users or about the movies. So instead, what we're going to do is we're going to flip this problem on its head, and we're going to try and estimate these matrices, this L and R matrix, which is equivalent to estimating these topic vectors or feature vectors for every user and every movie based on our observed ratings. So these matrices, or these collections of topic vectors, are the parameters of our model. So going back to the regression course that we had, or the regression module that we had, we talked about models and their associated parameters and thinking about estimating those parameters from data. So this is a very similar notion. So we have data. What are our data? In this case, our data are our observed ratings. So those are the black squares. And our parameters are these user and movie topic vectors. Okay, so what we're going to do is we're going to estimate each of these from our observed rating. So only using these black cells, we're going to try and estimate these L and R vectors and resulting matrices. So how are we going to do this? Well, let's think of a metric for fit, just like we talked about in the regression module. If you remember, going back to that module, we talked about something called residual sum of squares. There we were talking about a house. It had some set of features, and then we had weights on those features. Those weights were our parameters, and we were predicting some house sales price. And then we compared with the actual sales price, and we looked at the square of that difference, and we summed over every house in our data set. Well, in this case, the parameters of our model are L and R, and our prediction, our ratings hat, is going to be LU RV, this notation of doing this element-wise product and summing, and that's our predicted rating. And then our observed rating is rating UV. And what we're going to do is look at that difference, the difference between our observed rating and what we're predicting with our parameters LU and RV, and we're going to square that. And we're going to say our residual sum of squares of our parameters L and R is equal to this, and then we're going to sum over all movies that have ratings. So we're going to include all UV pairs where rating, let me use U prime, V prime to distinguish it from the specific U and V example I gave here. So we're going to add in all U prime, V prime pairs where rating U prime and rating V prime are available. And where are these available? They're the black squares, just to remember this picture here. Okay, so what I'm doing is I'm taking a given L matrix and R matrix. I'm looking at my predictions. So I'm looking at, and then I'm going to evaluate how well I did on all these black squares. So I'm looking at how well the L and U that I'm using fit my observed ratings. And then when I want to go to estimate L and R, just like when I wanted to estimate the weights on the regression coefficients in the housing value prediction problem, I search over, in this case, all the user topic vectors and all the movie topic vectors and find the combination of this huge space of parameters that best fits my observed ratings. And so the reason this is called a matrix factorization model, so that's really key. This is called a matrix factorization model because I'm taking this matrix and approximating it with this factorization here. Okay, but the key thing is the output of this is a set of estimated parameters here, and unfortunately I've just written over this very, very, very key point. So I apologize for that. Let's pause for a second so you get the writing. And now I'll just say in words, this next animation is saying that there are a lot of very efficient algorithms for doing this factorization. And we're going to talk about them in great extent in the recommender systems or matrix factorization course later on. But then, okay, so very efficient algorithms for computing these estimates of L and R. How do I form my predictions? How do I fill in all these white squares, which was my goal to start with? Well, I just use my estimated L hat U and R hat V, and I form my prediction just as we described when we assumed that we actually knew these vectors. Okay, well, matrix factorization is a really, really powerful tool, and it's been proven useful in lots of different applications. But there's one limitation, and that's a problem that we talked about a little bit earlier of the cold start problem, where this model still can't handle this problem of what if we get a new user or a new movie. So that's a case where we have no ratings, either for a specific user or a specific movie. So that might be a new movie that arrives or a new user arrives. So this is a really important problem, and one that, for example, Netflix faces all the time. How do we make predictions for these users or movies? Okay, so we saw in our feature-based classification approach that we were able to handle cases where we might have very limited user data. And on the other hand, in our matrix factorization approach, we saw that we were able to capture relationships between users and items, and in particular, learn features of those users and those items. And the question is whether we can have some integrated approach to get the benefits of both worlds. So importantly, the features of our classification-based approach, or something like that, can capture things like context, time of day, what I just saw, user information, past purchases, whereas the features that are discovered from matrix factorization can capture groups of users who behave similarly. So for example, women from Seattle who teach and are also moms. Okay, so a question is how we combine these two different approaches. Well, it's very straightforward. What we can do is we can take a new user for which we have no past purchase information, and we can use just features specified by that user, such as the person's age, gender, and so on, to predict the ratings that that person might have. Likewise, as we get more and more data from that user, we can weigh more heavily on our matrix factorization approach and use those learned features more strongly when we're forming our recommendations. So it's very simple to think about combining the ideas of a user-specified feature-based model with our learned features from matrix factorization, and gradually switch between the two depending on how much data is available from each user or for each product. And this idea of blending models is really popular. And one example of where it's really been shown to have impact in recommender systems was this classic example that we mentioned at the beginning of this module of the Netflix competition. So this competition was a competition for who could provide the best predicted ratings for users on Netflix. And the dataset consisted of 100 million different user ratings of movies. There's almost 18,000 different movies, nearly 500,000 unique users, and the goal was to predict 3 million ratings to the highest accuracy. And the prize was $1 million. So there were a lot of people very interested in competing for this prize. And what we see in this table here is the leading team, and their model actually blended over 100 different models to get their performance. And so this type of ensemble approach we're going to discuss more in the classification module. But this notion of combining models to get performance that exceeds the performance of any of the individual models is a very common and very powerful technique. So we've talked at great length about how to form predictions using different types of recommender systems. But a question is, how do we assess the difference in performance for these different systems we might consider using? Well, imagine we want to recommend products to a new parent, and this is the set of all possible products that we might recommend. And a user likes a subset of these products, which are represented by these magenta squares. And our goal, of course, is to discover the products that the user likes from the purchases that they've made, because we don't actually know which products they like. That's our goal, okay? So a question is, why don't we just use something like classification accuracy to measure the performance of a recommender system? So in this case, we could think about just counting how many items we guessed that they liked versus they did not like, and compare that to how many of those items they actually liked versus did not like. So Carlos talked about using that type of metric when he was talking about the sentiment analysis case study. But the issue here is actually multifold. One is the fact that we really care more about what the person liked than what they didn't like, and often we're faced with very imbalanced classes. So for example, there are lots and lots and lots of products out there, but typically a user is only going to like a very small subset of them. And so if we use this type of metric, we can get very good accuracy by just saying that the user won't like any of the items. So not recommending anything will get pretty good performance according to this metric. But another issue is something else, which relates to the costs of making these different decisions. So often we're going to assume that the user has a limited attention span, and so we can only recommend a certain number of items for that user to look at. So there's a much larger cost if out of this very small set of items we're allowed to recommend to this person, there's no liked item. That has a much higher cost than if we miss some of the user's liked items in this set of recommended products. So instead, we're going to talk about a different metric, or different metrics, which are called precision and recall. Let's start by discussing recall. So for a given recommender system, it's going to recommend some set of products to me. And I'm highlighting those by the colored pictures. So this is a recommended item, this is a recommended item, this is a recommended item, and so on. Whereas the grayed out pictures are items that were not recommended for me. Okay, so I haven't done a comprehensive annotation here, but hopefully you get the picture. And when I'm measuring recall, what I'm going to look at is I'm going to look at all the items I liked, so all of these magenta boxes, and I'm going to ask how many of the items that I liked were actually recommended to me. And so I'm going to compute that fraction. So let's do that. So each of the magenta boxes, so here's one that was recommended to me, two that were recommended to me, three that were recommended to me out of 5 items that I like. So the recall is 3/5. And so recall is going to measure how much a recommended set of items cover the things that I'm interested in, the things that I actually like. On the other hand, there's something called precision. And when we talk about precision, what we're going to look at is we're going to look at all of the recommended items. So when we were talking about recall, our world, when we were measuring this fraction here, was looking at the magenta boxes. That was the world that we looked at. Everything else could disappear from the slide. But when we're talking about precision, we're going to look at all the recommended items. Then everything else can disappear from the slide. So the recommended items are highlighted by these green boxes. Okay? And what we're going to look at is out of the recommended items, if that's our entire world, what fraction of those items were items that I liked? Okay, so in this case, there are 1, 2, 3 items that I liked and were shown, and a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 items that were shown. So this would be the precision. And so when we're thinking about precision, we're thinking about basically how much garbage do I have to look at compared to the number of items that I like. So it's a measure of when I have a limited attention span, how much am I going to be wasting my efforts on products that I do not like? Okay, so I have a question for you guys, which is, how would you maximize recall? Remember recall, we just look at the magenta squares, we look at the liked items, and we measure how many of my liked items were actually retrieved, were actually recommended to me. Well, as the title answers, there's a very easy way to maximize recall. Just recommend everything. If you recommend everything, you're guaranteed to recommend the products that I like. So in this case, what would recall be? It would just be 1, because all 5 of the products I liked were recommended. So this is because there are 5 out of 5 products recommended. But what's the resulting precision of doing this? Well, it can actually be arbitrarily small, because if you have tons and tons and tons of products out there, and if I like only a very, very small number of them, then if you recommend everything, I'm going to have very small precision. So let's just say this is small and maybe very small. So that's not really a great strategy. On the other hand, what would be the optimal recommender? What's the best recommender you can imagine? Well, the best recommender is one that recommends all the products I like, but only the products I like. So everything that was not liked was never shown by the recommender. So that would be great. No wasted effort, capture everything I like. Gonna make lots of money with this recommender system. What's the precision and recall? Both are 1 in this case. And you can go through and verify that using the equations from the previous slides. Okay, so now let's talk about how we can use these metrics of precision and recall to compare our different algorithms that we might think about using. And to do this, we can draw something that's called the precision recall curve. And let's start by talking about what these curves are going to represent. And what the curves are going to represent is for a given recommender system. What I'm going to ask you to do is I'm going to ask you to vary the threshold on how many items that recommender system is allowed to recommend to me. So I'm going to rank, for example, all the baby products on Amazon, and I'm going to allow you to recommend just 1 or 2 or 3 and so on. And so that's a threshold that you're varying, and that's going to trace out this curve. And what would this curve look like for our optimal recommender, where we only recommend products that I like? Well, what's the precision when I recommend just 1 product? Well, we know that's a product I like. And so my precision, my world is just that 1 product, and I liked it. So my precision is 1. And what's my recall though? If I have, let's say, 10 items that I liked, and I've only uncovered 1, well, it's 1/10. And likewise, as I'm increasing the number of items I show, my precision always stays at 1. I'm only recommending products I like, but my recall is increasing because I'm covering more and more of the items that I liked. So eventually we will hit this 1, spot. So the optimal precision recall curve is this line here. Okay, but let's talk about what the curve might look like for another more realistic recommender. I guess before that, let me just annotate that this is our optimal recommender. Now let's go on to look at perhaps a more realistic recommender and what it would look like. Okay, well, the first product we recommend might not be a product I like, or it might be, so it's going to start somewhere on the precision axis. And then eventually, at some point, when I vary the threshold enough, at some point, hopefully, I will recommend some product I like, so both precision and recall are going to go up. Then what tends to happen is we add a product that I don't like. So at that point, what happens? Well, my recall stays exactly the same because I haven't recovered any more of the items that I'm interested in, but my precision drops because now I'm looking at a larger world, a larger set of green squares. So my precision goes straight down, but my recall stays the same, and you tend to get these very jaggedy looking curves where you get these drops in precision, then these increases in precision and recall. And I'm going to draw it. It won't be completely accurate here, but it looks kind of like that. Typically something like this would be a precision recall curve. Okay, so this is an example of a more realistic system. This is another recommender system compared to our optimal. Okay, so now that we know how to draw these precision recall curves, we can talk about comparing our different algorithms. How do we know which one is best? Well, we know that we like precision and recall both to be as large as possible. And what's the best that it can be? We talked about the optimal recommender being that curve. But then when we look at our other curves, which are these jaggedy looking things, one doesn't have to strictly dominate another. They might do different things at different points. So one curve is not necessarily, let me actually erase that, do it in a different color so it's a little bit clearer. It's not that one is always going to be better than the other. Maybe we have another one going here. So in this case, how do I think about comparing these different algorithms and choosing which one is best? Well, like I said, we want precision and recall to be as large as possible, but one thing we can measure to compare these is, in general, which one is doing better than the other. And what's a way to think about that? Well, we can think about the area under the curve. So we can look at, for example, all this area under this blue curve. And we can compare that to, for example, the area under this red curve, green, if I can remember my colors, the area under the green curve. And I can say which area is larger. And that is one proxy for which recommender system is doing a better job. So that's this point here, that a metric we can use is something called area under the curve, which measures exactly what I drew below. But you might not care about how the recommender system is doing across all possible performance situations. Instead, you might be in a situation where, let's say you have a website and you know, based on the real estate of that page, how many items you can display. So maybe you can display 10 different items to recommend to the user. Or you know what the attention span of the users are in general, and you want to limit how many products you recommend to 20 products or something like this. So in those cases where you specifically know how many products you're going to be recommending, you care about what your precision is at that number of products recommended, because you want that precision to be as large as possible for the constraint of recommending that number of products. And so these are two examples of metrics you might use to compare between different algorithms using this notion of precision and recall. In this module, we talked about a notion of collaborative filtering and a couple different recommender systems for implementing that idea, where we leverage the types of other products people purchased to recommend other products. And we explored this notion of having some set of customers and products and understanding relationships between these in the context of a product recommendation task, thinking about movie recommendation. And in the IPython notebook, you guys explored this very concretely with an implementation of a song recommender. Once again, let's revisit this machine learning workflow, but in the context of recommender systems. In this case, what's our training data? Well, it's our user product ratings table. And what we're going to do is we're going to extract some set of features, which in this case are a user ID, product ID pair. And the goal here is to predict the rating that some user would give to some product. So user ID, product ID rating. So this is our predicted rating y hat. If we're specifically looking, and I guess I should mention that what is the model that we're looking at? The model is, for example, we talked about many different models, but one we're going to talk about quite extensively in the matrix factorization course is matrix factorization. And matrix factorization has some set of parameters, w hat, which are the estimated parameters, or that notation represents estimated parameters. And what are the parameters of matrix factorization? Well, it's a set of features for every user, and it's a set of features for every product. Okay, so these are our parameters. But we also talked about a featurized version of matrix factorization. So in that case, in addition to our features being the user ID and product ID, we might also consider other things. Like we might have a list of other features like the age of the user, the gender of the user, a description of the product, and so on. And in that case, we would also add weights on these features. So let me just add some extra set of, I'll call them W0 to make it different than this W, some other set of weights here that are also parameters of this model. Okay, again, we'll get into this in a lot more detail in the course on this, but the idea is we're going to take our predicted rating and we're going to see how well our model is fitting the data. And the way we're going to do that is we're going to take our actual data, our real ratings, so these are actual ratings that are in our training data set, and we're going to compare to the predicted ratings. Okay, so one metric we talked about to measure the error between the predicted ratings and our actual observed ratings was residual sum of squares, just like in regression, but there are also other metrics we could consider, and we can talk about those more later. But the point is that from some notion of error between our predicted values and our observed values, we're going to have some machine learning algorithm. Again, we're leaving this for the actual module on matrix factorization to describe what this algorithm is, but what it's going to do is it's going to iteratively update our features for the user and for the product until we get good agreement between our predicted ratings and our actual observed ratings. Okay, so in this module, you've learned how to do collaborative filtering in practice. So now you can go out and actually implement a recommender system. You can do a gift recommender for your family, which will make holiday shopping really easy. Or you can build a new song recommender that's even better than the one that we demoed. So lots and lots of cool things you can do with collaborative filtering.
In this module, Emily showed us how to build product recommenders and the algorithms associated with recommender systems. Now we're going to build a notebook to recommend songs we might want to listen to. This is going to be really quite cool. Okay, so this is going to be we're going to rename our notebook here. This is the song recommender. So again, I'm going to hide the header and hide the toolbar to show us a little more space. And as usual, we're going to start by importing GraphLab. Get us started here. And the first thing that we're going to do is load some music data. So we're going to load music data. This is a really cool data set. It's called the million song data set. And we're going to create a variable called song data. It's going to store it. and we're going to have a GraphLab S-frame where we're reading it, and this is a songdata.gl. So here we are, we're reading it, and so let's start doing a little bit of data exploration. So let's do some exploring of our friend data here, music data. So first thing that we're going to do, as usual, is take the song data and take a look at the first few lines of this table. And so here's what the song data looks like. A user with a user ID listened to a song once or twice. This is the title of the song. This is the artist. And this is the song itself. The title is the title of the record, actually. And so, as we can see, we just have a table that shows us how often each person listened to different songs. And then we're going to use this to build a recommender that finds out other songs you might be interested in listening to. And we're going to explore a couple of different types of recommenders, as Emily shared with us in the module. So as usual, I'm going to, I like showing the histogram on the notebook itself. So I'm going to do graphlab.canvas.setTarget, and I'm going to say IPython notebook. And then after we've done that, I'm going to take my song data and I'm going to look at a particular column, let's say the song column, and type .show in it, which is going to show me a histogram of the different songs and how often they're playing. And here we are. So this is the different songs by title, and you see how this song here was played 5,970 times. This Bjork song was played 5,281 times. This song here, this is a Brazilian song, TVC by Cartola, 3,185 times. So some people really like their songs and they play them a lot. So this is the kind of data we're looking at. And if you take a quick look at the song data, you'll see at the length, you see we're talking about here 1.1 million songs. So million song user pairs. So this is ratings, song ratings. And this is what the data set is, a pretty large data set, but we're going to do some things together on this large data set right here. So let's do a little bit more exploration. So we said for each user, there's 1 million, about a million ratings or a million number of listens. Let's see how many users are involved here. So I'm going to, let's say, count number of users. So in doing this, I'm going to show you another little trick which is useful as you're exploring your own data set. So I'm going to create a new array here for users, and this is going to take the song data that we have and look at the user ID column, and I'm going to ask you apply the unique command. And what the unique command does is select out of all these users, just shows the unique different users that we have, just all the unique ones. And so if I ask for the length of users, you should see that we have 66,346 unique users in this data set with 1 million different song, you think about ratings, but number of times they listen to some song activity rows. Good. So this is our data set. Then the next step for us is to create a recommender system. So here we go. Let's go ahead and create a song recommender. So as usual, we're going to start by doing a train test split. So I'm going to take the training data, the data is split into train and test data. And we do that by taking the song data. We're going to do a random split on this data set, 80% for training, 20% for testing. And again, we're going to set the seed to 0 so that if you do this at home, you get exactly the same answers as I got. Okay, we've done that split, and now we're ready to train some recommender models. So just following the lecture a little bit that Emily gave, the first recommender model we're going to train is a simple popularity-based recommender. So this is what many websites do. For example, when they say, here are the most emailed stories, or this is the most purchased products, this is what's most popular, the most common hashtags on Twitter today. Not a particularly great model, but it's used a lot. So let's train our famous popularity model. We're going to call it popularity model. And all I have to do now is call graphlab.popularity recommender. So this is a particular recommender, and I type create next to it. And as you remember, create is the verb here that actually creates a recommender. And I'm going to give it my training data as input. And this model takes a little bit of information. So let me just walk you through it. You have to say what column is the user ID in the data set. So in our case, that column is called just user ID. User ID. Then we need to say what column is the item ID. So the item ID is in our case, the product. So users and products, but we don't have exactly a product in our item. Our item here is songs. So item ID is equal to song. And now when I hit enter, it creates, and it was very quick, created a simple popularity-based recommender system. So let's just make some predictions. So in our next step, we're going to use, let me just scroll down a little bit, use the popularity model to make some predictions. So for example, let's take this popularity model and let's ask it to recommend for a particular user. So I'm going to recommend some songs this particular user like. So this recommend function takes a list of users, and we're just going to give one to the list right now. And if you remember, we had that users array. I'm just going to give you the first person in that users array and execute. So what do you recommend for this person? A song by Harmonia, a song by Bjork, King of Leon, and so on. Now look at this very carefully. Dwight Yoakam, this is what's being recommended by user 0. Now let's see what this model recommends for user 1. So again, we're going to take popularity model, and I'm going to call recommend. And again, I'm going to give it a list of users, but instead of giving a user 0, I'm going to give user 1. Now before I click enter here, shift enter, just stop and think, what am I going to get back out of the popularity model? Well, everybody gets recommended exactly the same things because you're just recommending the most popular items. So this person also gets recommended Harmonia, Bjork, Dwight Yoakam, King of Leon. So basically, not that exciting. Everybody gets recommended the same things. This is a problem with this model. Now, if let's in contrast, let's make it a more personalized, a model that's more personalized, as Emily described. So next, we're going to build recommender, a song recommender with personalization. So let's call it personalize model. And all we're going to do is repeat the line that we had earlier. So GraphLab dot, instead of being the popularity model, let's use that item similarity recommender. So remember we talked about item similarity in the module. We can do an item similarity dot create, and let's see what happens. So here, just like before, we have to give it a training data. We have to tell it what the user ID column is called, which in this case was user ID. And you have to tell it what the item ID column in this case, which is called song. So instead of the popularity model, we now built an item similarity model. And here we go, it's done. So let's start applying it. So applying the personalized model to make song recommendations. And here we go, let's apply it. So let's start with the couple users that we had before. So for example, if you take the personalized model, and we call recommend on it for users, for that first user, so users of 0, you'll see that no longer does it recommend Bjork and a few of those others that everybody got, but recommended Dr. Feelgood, Elisete Cardoso, another Brazilian song, Ween, Subhumans, and so on. It's kind of an interesting thing. So pretty cool. Let's see what user 1 got, because it's a personalized model. So personalized model, the recommend for users, and again, it's a list, but I'm just going to put one element in the list, so user 1, and you'll see that now it recommends something totally different. Florence and the Machine. And somehow this user really likes Florence and the Machine. It just recommends that again, and Apocalyptica, and so on. So as you can see, now the model is really personalized. And you can do some really fun things with it because it's personalized. Not only can you say for a particular user what songs, other songs they should listen to, just like we did in recommendations, but we can also take a song and ask what other songs are similar, are liked by similar people. So people who like the song also like this other song. So we can do that by calling personalized model dot get similar items. So get similar items, you give it a list of items and it finds similar ones. So for example, if I really love the song With or Without You by U2, I mean, I really actually like the song. It's pretty cool. You'll see other songs it recommends, all by U2. I still haven't found what I'm looking for. Hold Me, Thrill Me, Kiss Me, Kill Me, Window in the Skies, Vertigo, Sunday Bloody Sunday, Bad, A Day Without Me, Another Place, Walk On is a nice song, Get On Your Boots. So all U2 songs. If you like one U2 song, you like other U2 songs. That's pretty typical. Now, another thing that I enjoy, so if I take this personalized model and I'm gonna get similar items, so you can get also similar users. So for a user, find other users that like this one, but like her, but here we're gonna get similar items. And the list I'm gonna give is a little different. So this is another song I kind of like. It's called Chan Chan, and it's I like the live version, and it is by Buena Vista Social Club. Now, if you don't know the song, if you know the Buena Vista Social Club, you should. It's awesome, awesome, really cool. And so if you like Chan Chan by Buena Vista Social Club, Cuban Band, you also might like other Buena Vista Social Club songs, Amor de la Loca Juventud and others. You might also like this, Diferente by Gotham Project. Gotham Project, Argentinian band, really cool one. You might like Gypsy Kings, flamenco band. This all makes a lot of sense. Another song down here by Gotham Project, Criminal, which I kind of like as well. So we've now seen these models in action, and we've done this, what we call a kind of qualitative, just kind of anecdotal qualitative exploration. Let's do a more quantitative comparison between the personalized model and the popularity model. So now we're going to do a quantitative comparison between the models. So as we explored with Emily in the lectures, when you're comparing recommenders, a good metric to use is precision recall. So can we explore the precision recall curve for these two models? So here, we're going to use, we discussed matplotlib earlier in a different notebook. So we're going to call matplotlib here, and I'm going to add this little command inline to make sure the matplotlib actually prints into the recommender here. So into the notebook. So matplotlib, and what I'm going to do is compute model performance. This is the variable that I'm going to create, and there is this method in the recommender libraries from GraphLab Create. Is a set of utilities for recommenders, and one of those is really cool. It's called compare models, which allows you to compare different recommender models and understand how they do. So I'm going to compare different recommender models on our test data that we separated. And the models I'm going to compare are our popularity model and the personalized model. So here's the list of the two models I'm comparing. I could compare more, but I'm just comparing those two. And I'm going to say, I'm going to add a little parameter here called user sample, where I'm going to just sample a small fraction of the test data. So user sample equals 0.05, because on this machine, building this precision recall curves takes a little while, and I want it to be fast so we can look at it together. So it does it pretty fast. It's comparing, it's evaluating first the performance of the popularity model, that's model 0, then the performance of the second model, model 1, which was the personalized model, and finally what we get here is the precision recall curves, the last thing that we saw in the lectures. And this compares the recall and precision of these two models, the personalized model in green and the popularity model in blue. And the closer you are to the top here, the better. And you see that adding personalization significantly improves the performance of our recommender. So personalization is great, just recommending popular items, not so great. And so with this, we've built a song recommender, and we explored it. We saw that it recommended cool songs for somebody like me who likes U2 and Buena Vista Social Club. But of course, you can go and explore all the things that you might like, and see what else other recommendation songs you can come up with. Today, we're going to talk about one of the most exciting things to be happening in machine learning over the last few years. It's a new area called deep learning. In particular, we're going to talk about a particular use case of this area, related to shopping for products just based on image similarity. Great, we talked about an application of finding cool shoes or dresses just based on image features. The technique that we're going to use today is called deep learning, and in particular is based on something called neural networks. But before we get there, let's talk about data representation. We discussed things like TF-IDF and bag-of-word models, but how do you really represent data when it comes to images? These are called features, and this is a key part of machine learning. So typically, when we talk about machine learning, we're giving some input. Let's say we're doing classification. We talked about sentiment analysis. You're giving a sentence, it goes through a classifier model, and we decide if that sentence has positive or negative sentiment. In image classification, the goal is to go from an image, this is my input, the pixels of the images, to a classification. In this case, this was my dog, and I want to classify it as a Labrador Retriever as opposed to other kinds of dogs. So as we discussed, features are the representation of our data that's used to feed into the classifier. There are many representations. So for example, with text, we talked about bag of words and TF-IDF. With images, there's a lot of other representations, and we'll discuss a few more of those in this module. But today, we're really going to focus on neural networks, which provide a nonlinear representation for the data. Now, let's go back to classification and just do a little review. We discussed linear classifiers, which create this line or linear decision boundary between, say, the positive class and the negative class. And that boundary is stated by the score, W0 plus W1 times the first feature, X1, W2 times the second feature, X2, and so on. On one side, on the positive side, the score is greater than 0, and on the negative side, the score is less than 0. So if I have this nice score function, I can separate the positives from the negatives. In neural networks, we're going to represent such classifiers using graphs. And so here we have a node for each feature, X1, X2, all the way to the dth feature, XD, and a node for the output Y, which we're trying to predict. So the first feature, X1, is multiplied by the weight W1, so I'm putting that weight on the edge. X2 is multiplied by the second weight W2, I'm going to put it on that edge, all the way to XD, which is multiplied by the weight WD, which I put in the last edge. And the last weight W0 doesn't get multiplied by any feature, but it gets multiplied by the number 1, so we put it a little 1 at the top, multiplying W0. And so if you imagine multiplying the weights W0 through WD with the features X1 through XD and the coefficient 1, you get the score. And when the score is greater than 0, we declare the output to be 1, and when the score is less than 0, we declare the output to be 0. This is an example of a small one-layer neural network. So we describe the small linear classifiers as a neural network, as a one-layer neural network. What can this one-layer neural network represent? Let's take the function x1 or x2. Can we represent that using a small neural network like this? Well, let's define that function a little bit more formally. So what we have is variables x1, x2, and the output y. And there's some possibilities. X1 can be 0, X2 can be 0, and since it's X1 or X2, the output Y will be 0 in this case. When X1 is 1 and X2 is 0, the output is 1. When X1 is 0 and X2 is 1, the output is 1. And similarly, when they're both 1, the output is 1. So we want to define a score function such that the value is greater than 0 for the last 3 rows, but it is less than 0 for the first row. How do we do that? So for example, there are many ways to do it actually, but if I put a weight of 1 on each one of the edges, x1 and x2, and we think about the score of the first row is 0, and the score of the other rows are greater than 0. So we want to add a little bit of separation, so we might put a negative value on the first edge, let's say minus 0.5. And so let's see what happens to the score. When x1 is 0 and x2 is 0, then the score becomes minus 0.5, and yay, I have something less than 0, and my score is correct, my output is correct. When x1 is 1 and x2 is 0, I get a score of 0.5. Similarly, when x1 is 0 and x2 is 1. And finally, when they're both 1, I get a score of 1.5. So with the simple weights on the edges, I represent the function x1 or x2. Now, can we represent the function x1 and x2? Well, similarly, we can put weights 1 and 1 on the edges x1 and x2, but in this case, we only want to turn it on when both x1 and x2 have value 1. So instead of putting minus 0.5 on that top edge, we put minus 1.5. And if you fill out the table, just like we did with the first example, you notice that we now represented the function x1 and x2 using a simple neural network. So a one-layer neural network is basically the same as the standard linear classifiers we've been learning about in this course so far. So what can linear classifiers not represent? We said it can represent x1 or x2, and it can represent x1 and x2. But what's a function, a very simple function they cannot represent? Well, here's an example. There is no line that separates the pluses and minuses in this example. This function is called the XOR. I like to call it the counterexample to everything. So whenever you're trying to find a counterexample, first thing to try is XOR. Now, for this case, the linear features that we described are not enough, and we need some kind of nonlinear features. And this is when neural networks come to play for reals. And we'll see an example of that. So let's review what XOR is. So XOR has value 1 when either x1 is true and x2 is false, so not x2, or when not x1, so x1 is false or 0, and x2 has value 1. So how can we represent this with a neural network? Well, let's call this first term z1 and the second term z2. What we're going to do is build a neural network to represent not directly the inputs x1 and x2 to predict y, but they'll predict its intermediate values z1, z2, and then those are going to predict y. So let's take z1. How do we represent a neural network, one-layer neural network that can predict z1? We discussed that a little bit, but here goes. It's a little bit different than the case, the end case from before. Since we have to negate, we say not x2, we put a minus 1 on that edge, and we put a plus 1 on x1 and the minus 0.5, and there we now have a representation for z1. Similarly, for z2, we put a minus sign on the edge x1, this edge here, x1 to z2. We put a plus 1 on the edge x2 to z2, and a minus 0.5 on the constant edge. And now we represent z2. And the last step, if z1 and z2 exist, all we have to do is OR them. And we already know how to OR two Boolean variables. It's just 1, 1, minus 0.5. And this is an amazing time for us. We've now built our first deep neural network. Not super deep, has 2 layers, but it is a little exciting. We just built our first neural network. It was a 2-layer neural network, but in general, neural networks are about these layers and layers of transformations of your data. And we use these transformations to create these nonlinear features, and we'll see some examples of that in computer vision. Now, neural networks have been around for about 50 years, about as long as machine learning has been around. However, they fell in disfavor around the 90s because folks are having a hard time getting good accuracy in neural networks. But everything changed about 10 years ago because of 2 things that came about. First, there was a lot more data. And because neural networks have so many more layers, you need a lot of data to be able to train all those layers. They have a lot of parameters. We'll see a really exciting neural network of 60 million parameters. So we need a lot of data to train them. So we recently have come about lots and lots of data from a variety of sources, especially the web. Now, the second really great change that made deep neural networks possible is advances in computing resources. Because we have to deal with bigger neural networks and more data, we need fast computers. And GPUs, which were originally designed for accelerating graphics for computer games, turned out to be exactly the right tool to build and use neural networks with lots of data. So because of GPUs and because of these deep neural networks, everything's changed. And now they've had a lot of impact in the real world. Deep learning is exciting because it learns these complex features of images, and as we discussed earlier, they've had tremendous impact over the recent years on a variety of computer vision applications. Let me show you a couple early examples. So on the top of the slide here, what you see is an example of identifying traffic signs based on neural networks. So this is a data set of German traffic signs, and the idea is for every image, identify what sign it is. And they were able to get 99.5% accuracy using a deep neural network, which is pretty cool. On the bottom there, you see an example that came out of some work from Google on identifying the house numbers based on what's called street view data. This is the data that Google uses driving around cars and photographing all sorts of streets around the world. And if you see, the images are pretty complex, and still they were able to get 97.8% accuracy on the per character level. Now these were exciting results, but the one that changed everything, that really excited the field, happened in 2012. So for many years, there was an image competition called ImageNet. And in 2012, the ImageNet competition included 1.2 million training images from about 1,000 different categories. And the idea was, can you classify this image? Is it not just a dog, but is it a golden retriever or a Labrador? Very, very fine level detail. Now, there's many teams competed. These were the top 3 teams. The team called Oxford VGG, which got pretty decent accuracy. So if you look at their top 5 guesses, can you get it right in 5 guesses? They were getting only about 25% error. There's a team called ISI that did a little bit better. And those are using traditional techniques like the SIFT one, a little bit more elaborate, kind of like that. Now that year, there's a team called Supervision. That team used a deep neural network and had a huge gain over the competitors. And that performance really sparked a lot of the excitement of using deep neural networks in computer vision, because they didn't have to just use hand-coded features, you'd learn them automatically. Now, that neural network that won the competition with the Supervision team was called the AlexNet neural network. And I'm showing here an image from their paper. And that neural network involved 8 layers, 60 million parameters, and was only possible because of new training algorithms that could deal with lots of images and lots of parameters, and a GPU implementation that would really scale to large data sets. So we saw that deep learning had a tremendous impact on that ImageNet competition, which allowed them to take 1.5 million images, train the deep neural network, and get amazing performance in predicting 1 of 1,000 different categories. So let's go ahead and show you a little demo of what kind of categories we're talking about and how cool the predictions were. So here's an example. It was the AlexNet trained on the ImageNet dataset, which we then deployed as a service that can be queried from this website. And so every time I click on an image, it gets sent to that service, which actually runs on a GPU, so it's fast, and it comes back for prediction. So if I click on this particular image here, it gets sent to a service that's actually hosted on Amazon AWS. It comes back for prediction. Here it's hidden, but when I click on it, it tells me what prediction is. So if I show you this image, it might be unclear what that image is, but if I click on it, it says parking meter, and it turns out to be the right label. The second best here prediction was padlock, which you can kind of see kind of a padlock, but really parking meter, got it right. So that's really quite cool. Let me show you another example. So for example, this one, it gets shipped off to that service on Amazon AWS, comes back for prediction, and here my prediction is screen, monitor, oscilloscope, and you see it's a monitor, but I don't know the difference between a screen and a monitor is, but that's okay. So there's various images here. I'm just going to click on a few. So for example, if I click on this one over here, it gets sent up. It's really sure, it really thinks it's a spoonbill. It turns out to be a spoonbill, which is great. Lastly, I'm going to click on this one over here, and that image gets sent to that service, uses deep learning for GPU, and it says it's a beer bottle or pop bottle. The true label is beer bottle. And now these are all images in the original ImageNet dataset. Let me show you an image that was not in the original ImageNet dataset. I click on this one here. It gets sent to that service on AWS that we're hosting there. Comes back for prediction. It says Labrador Retriever. This is my dog. This is the lab in GraphLab. And this is the dog over here in data. And so, as you can see, even for images that were not in the original data set, you can still get pretty interesting predictions. Now, in your capstone, you're going to build a service not for predicting images here, but for recommendations with deep learning for product images and text, and host it as a service. And you'll be able to get a website like this that anybody can play with, use, and really see the power of the machine learning that you've been learning about. Now, neural networks provide some exciting results. However, they do come with some challenges. So, on the pro side, they really enable you to represent this nonlinear complex features, and they've been having impressive results, not just in computer vision, but in some other areas like speech recognition. So, systems like Siri on the phone and others use deep neural networks behind the scene, as well as some text analysis tasks. And there's potential for much more impact in a wide range of areas. Now, they do come with some challenges. And to understand those challenges, we need to talk about the workflow of training a neural network. So you need to start with lots and lots and lots of data. And that data has to be labeled. Every image has to have, what dog was in the image? Is it a Labrador? Is it a poodle? Is it, golden retriever, Chihuahua, and so on. And that requires a lot of human annotation. That can be hard. But we start with lots of images. We feed it, we split them into train and test or validation sets, as we discussed. And we learn a deep neural network, and that can take quite a while. But once we validate, we realize that that complex 8-layer structure with 60 million parameters wasn't exactly what we needed, and we need to revise it, or we need to adjust parameters or change how we learn it, and we have to iterate again and again and again. And in fact, to get that winning neural network, the AlexNet one, they really needed to connect various layers with different representations and lots of complexity in the learning algorithm. So that was hard. So although there's some great pros, neural networks, deep neural networks come with some cons too. They require lots of data to get great performance. They're computationally expensive. Even with GPUs, they can be computationally expensive. And they're extremely hard to tune. So you have a lot of choices in what layers you use, how many layers, what parameters you use, and that can be really hard. So if you combine the computational choices and costs with so many things to tune, you end up with an incredibly hard process for figuring out what neural network to use. We've now seen how cool deep learning can be. We can apply in a wide range of areas and get really high accuracy by learning really detailed features of our data, and how neural networks can support that. We've seen how it can be applied for various tasks in image analysis, in computer vision. Let's now revisit the block diagram that we saw summarizing regression and classification and other machine learning tasks, and how it can be applied here for computer vision, for deep learning. So in particular, let's talk about deep features for classifying images. So deep features for image classification. The input here are pairs of images with their labels. So the labels that we've looked at were things like, whether it's a cat, a dog, a house, or some other object in the image. And now we feed that through the feature extractor. And in this case, we're using a deep learning model as a feature extractor. So the output here are what we call the deep features for this particular image, for every image. And now we feed in this images representative features through a machine learning model, where we use a simple classifier like logistic regression in here. Say logistic regression as an example. And the output is our predicted labels. Predicted labels. And so we're going to feed in our predicted labels y hat and the true labels y into our measure of quality. So y and y hat. And the measure of quality depends on your task. For this task, we use classification accuracy. And so the parameters w hat are really the parameters of the weights of the logistic regressor. So these are our weights on features. And what the machine learning algorithm is going to do is take the classification accuracy, try to make it a little better by changing those weights w hat and updating them. We've now seen how deep learning can give you really cool and exciting results for various tasks in computer vision. And we saw those applied both to classification and to retrieving of new images using raw neural networks as well as deep features. And our notebooks that we explored showed us that it's really easy to build such deep learning models and actually apply to a really cool machine learning task in computer vision, both in classification and image retrieval, which allows me to find exactly the kind of shoes that I'm really excited about. And with this, you'll be able to build a really exciting intelligent application that uses one of the most sought after techniques today in machine learning, deep learning. So in this deep learning module, we talked about two really cool things that you can do with deep learning. One is classify images, and the other one is retrieve images. And in both of them, we talked about deep features. So let's just go ahead and build a notebook for image classifications using deep features. So let's give this notebook a name. So this is going to be image classification with deep features. And I'm going to hide the header and the toolbar to get a little bit more space as usual. And we'll fire up, oh, actually, I just did a little typo here. So we will fire up GraphLab create. So let's import GraphLab. So here we go. So the first thing that we're going to do is load a common image analysis data set. So this is a benchmark data set called the CFAR10, and we select a subset of those where we just have 4 categories of objects we're trying to recognize. So I'm going to load the data set, and this data set has already been split into training data and test data, because in computer vision often that split happens a priori, so every researcher uses the same training set and the same test set, so the papers become more comparable. So I'm just going to load an S-frame that contains the data set. So graphlab.sframe, and for the training data, there's a directory here called image train data, and then for the test data, so I'm going to call that image test. We have another S-frame called image test data. Here we go. So we're loading these 2 data sets, and let's start by exploring the data a little bit. So exploring the image data. So what we're going to do is use Canvas. So I'm going to point Canvas to show it on the notebook, as we've been doing on several notebooks, so it becomes all one thing that we can take home. So I'm going to set graphlab.canvas. I'm going to set the target to be the IPython notebook. So it's going to print anything on the IPython notebook that we do. And let's start by taking a look at this training data. So image train, it has a few columns, but the column that we really care about here is the image column. And I'm just going to type .show on it, and we're going to take a quick look at that image column. And these images are not too large, so I'm temporarily going to increase the font here so you can take a look at the images. And so if you look at it, there's a bird, there's some cat, there's some dogs and some cars. So this subpart of the data set is all about cats, dogs, cars, and birds. So we're decreasing the font, and we're going to train a basic model on this data set. So the first thing that I'm going to do is not use the features, but just use the pixels of the image and train a classifier on the pixels of the images and see how well that does. So let's just go ahead and do it. So train a classifier. I misspelled it here. So train a classifier on the raw image pixels. So these are going to be my features, the raw image pixels, not those deep features. And so I'm going to call this the raw pixel model. And the classifier I'm going to use, I could use any classifier, the performance will be about the same. I'm going to use logistic regression, which is what we use also in the sentiment analysis notebook. And so in logistic regression, we're going to give it a data set. So this is going to be the training data set. So this is my image train. I'm going to tell it what the target is. So the target is a column in this data set called label. And that column has the label for each image. And I'm going to tell it what features to use. So in this case, the features are a column called image array. And so I'm going to run this. Wait, I must misspell module. Oh, yes, I forgot one thing and you should have reminded me. In GraphLab, create, the verb that you do to create a model is create. So GraphLab.logistic regression, logistic classifier dot create creates that classifier. So now it should execute. So we're using the raw image pixels to build a classifier. And just as a quick review, I don't expect that to be very good. But let's go ahead and do it. It just is done right now. So let's see how it performed. So the first thing that I'm going to do is just make a prediction with the model. So let's make a prediction with the simple model based on raw pixels. So I'm going to take some images from the test data set, and I'm going to see what the classifier says they are. So I'm going to say image, test, and let's look at the first three images. So images 0, column 3 goes image 0, 1, and 2. And I'm just going to look at those images, and I'm going to type .show on them just to show you what those images are. So here we are. The images, as I said, are a little bit small on the data set, but I'm going to make this bigger so you can see the images here are a cat, a car, and another cat. So two cats and a car. Car, cat, no, cat, car, cat. And so I'm just going to leave the font big so we can actually see the results. So now let's look at the labels for this image. So this is the test data, and this is elements 0 through 3. So the first one, 3. I visually said it was cat, car, cat, but let's see what the actual labels are. So the label column, and you'll see it is cat, automobile, cat. So it's automobile, not car, but same thing. Okay, so let's see what this raw pixel model predicts. So let me see what it predicts for this data set of 3 images. So the image test of 0 through 3. So the truth is cat, automobile, cat, and it predicts bird, cat, bird. So it gets all three wrong. It thinks the cat is a bird, it thinks the car is a cat, and it thinks the cat is the other cat is also a bird. So it got it all wrong. But this is only kind of a fluke qualitative thing. It could be that just the first few images it got wrong. So let's take a look at what the actual predictions are. So let's evaluate the model and the test data and see what the actual classification accuracy is. So evaluating raw pixel model on test data. So I'm going to take this raw pixel model, and I'm going to call evaluate. And what evaluate does is just goes and computes some of those errors, those error metrics. And I'm going to use the test set. And here you see the accuracy is only 46.8%. It's terrible. You have 4 classes, random guess is 25%, they're balanced. Here it gets 46%, not that exciting. So there's some more details there. The confusion matrix gets plotted. I'm not going to go through that, but at home you can explore those a little bit more. But just remember 46%. So the question here is, can we improve the model using deep features? Remember we talked about deep features. We explored those quite a bit in this deep learning module, how deep features using a technique called transfer learning can be trained on one domain, then applied to images in another domain to learn something with even a small amount of label data. So in this case, let's just take a look at the length of our training data, just to get a sense of what we have. We only have 2,000 images, so this is a pretty small data set. And so we can go ahead and see what we can do with just 2,000 training images, but using some deep features. So this is the steps that you take. So we're going to load a deep learning model that was pre-trained. And so here you can use graphlab.load model to load that model. And I have a model that was trained on the ImageNet data. It's over here. So it's called ImageNet model. And this model was trained with 1.5 million images, 1,000 different categories, a different data set, 1.5 million images. It was what we discussed, the AlexNet model. They got really amazing accuracies in 2012 ImageNet competition. So I pre-trained that model, and then you can use that model to create, in our image train, a new column called deep features. And in this new column, the deep features, what I'm going to do is take this deep learning model that we just loaded, deep learning model, and I'm going to apply a function called extract features. And what extract features does is extract those deep features. So does a transfer learning, taking features of learning in one domain and applies to a data set in a different domain. So this data set here is my image train data. So these are the two commands that you have to do. Pretty simple. Actually, let me decrease the font size so that it will be a little bit more visible. The two commands that you have to do to do the transfer learning. So take the ImageNet trained neural network and apply it to this CIFAR10 data set. Now, this computing deep features takes a few minutes, and so I'm not going to do this right now. Instead, I'm just going to tell you that our deep mod, if I show you the image train data, what I did was if I just show you the head, the first few lines, what you'll see is that you have an image ID, you have an image, which we've been looking at, you have the label, and you have a column for deep features. So I pre-computed that and I saved it inside the S frame. So it's already saved and pre-computed. And it also has another column image array that has the raw pixels that we use to train the raw pixel model. So the deep features are already in there, but if you run those two commands, you'll be computing them yourself on this data set or on any data set that you want. So let's go ahead, and now that we have the deep features, let's train a deep model. So given the deep features, let's train a classifier. So now we're going to train a simple classifier using the deep features. I'm going to call this deep features model instead of the raw pixel model. And the deep features model is also going to be just calling logistic regression. So dot create. And if you remember from lecture, we discussed that you can take those deep features and plug in a simple classifier at the end. In this case, we're just plugging in logistic regression. So as input, I'm going to give it the image train data. And for features, instead of using the raw pixel, I'm going to use the deep features. And finally, I'm going to tell it that the label, the target, the thing that I'm trying to predict here is given by the label column. And there you go. So now we're learning a classifier, and it's done here using, on those 2000 images only, using data from, using features computed in this deep neural network that won the 2012 deep learning competition. So now let's first explore the model, just apply it for some data. So we're going to apply the deep features model to the first few images of test set, just like we did with the raw pixel model. We're going to apply it in this case. So remember, we took the image test data and we looked at the first three images, so 0, 1, and 2, and here's what those images look like. And I'm going to type dot show and just remind you that we have a cat, a car, and another cat. And let's go ahead and just run this deep model to see what we predict. So I'm going to take my deep feature model and I'm going to predict on these three images. So image test of 0 through 3. And remember, cat, car, cat, and it says cat, automobile, cat. So basically, it got those three exactly right, which is exciting. So something that sucked, really did badly using the raw pixels, now using these deep features does well on those three points. It gets exactly right. But let's actually evaluate the deep model more formally. So what we're going to do next is compute the test data accuracy of the deep features model. And here we go. So how we're going to do that? We're just going to do deep features model dot evaluate, just like we did with the raw pixel model. Here we do dot evaluate, and as input we're going to give it the test data, so image test. And remember, the raw pixel model got 46% accuracy. It was bad. Here, by using deep features, we now get 78% accuracy, which is quite good. It's close to state of the art. Even if you had learned more data, it's quite good compared to the 46%. So the deep features provide you with a great tool for taking just a little bit small piece of data, running through the deep features, and get quite good accuracy at, say, doing image classification task here. we saw how deep features were great for image classification. They allowed us to get quite high accuracy, even with just a little bit of training data on a particular classification task, by first finding features from this deep learning model that won the 2012 ImageNet competition. So that was pretty exciting. But if you remember the motivation at the beginning, kind of the sample use case at the beginning of this module, we're talking about finding images of products that I like. You know, I like shoes. I want to find shoes that are similar to my shoes. I want to find images that are similar to the products that I care about. So instead of doing an image classification task, now we're going to take those deep features and do an image retrieval task. So let's go ahead and do that. Okay, so we're going to name our notebook. So I'm going to talk about deep features for image retrieval, and I'm going to hide the header and hide the toolbar so we can go ahead and get a little bit more space. And I'm going to fire up GraphLab Create, and I'm also going to load the CFAR 10 dataset, which is the same dataset that we loaded earlier when we talked about deep features for classification. So in this case, I'm just going to load the training set because we're just going to do retrieval in the training set. So let's start from there. So I'm going to call it image train, and I'm going to use graphlab.sFrame, and then as input, I'm going to give it the image train data. And just as a little reminder, if I look at this image train data set, .head, in this sFrame, we have the image ID, the actual image, the label, which we're not going to use for retrieval. We're not going to look at the label at all. The image array with the pixels, which we're also not going to use, but it already has the deep features pre-computed. In the notebook on deep features for classification, we looked at those lines that you need to compute that column deep features. Here, I'm just going to use those deep features. So this is going to be pretty simple. It will be similar to the document retrieval notebook that we did to find documents that were similar to Barack Obama, to Clinton, to Beckham, and others. So let's go ahead, and what we're going to do is train nearest neighbors model for retrieving images using deep features. So this is going to be pretty simple. We're going to call it the KNN model, just like we did with document retrieval. And we're going to use GraphLab's nearest neighbors toolkit, and we're going to call the create verb to actually create this nearest neighbors model. And just like in the nearest neighbor model, we're going to give it some data. So in this case, it will be my training data. I'm going to tell it what features to use. So the features that we're going to use are going to be exactly those deep features. And then, just as a reminder, you can give it a label ID. So the label here, we're going to use the image ID, which will then allow us to go back and find the images that correspond to the nearest neighbors. So now that we've created these helper functions, let's do this for another image here. This is one that I cheated a little bit. I found a car. And then we'll just try a few examples. So we found a car, and this car is image train, and it's the 8th image. So I just went image by image until I find a car, and then just so that you see, let's take the car image dot show, and we'll see the actual car we're talking about. And this is a red car. You see it right here, red car. And the question is, what are the nearest neighbors for that car? And that was this command that we did over here, get images from IDs, where we query the car. But I'm gonna kind of shortcut things a little bit. So I'm gonna say get images from IDs, where I'm gonna take my KNN model and give it as input the car image. So KNN model, I'm gonna query that car image, and the output is going to be a list, an S frame, and I'm gonna select the image column of the F frame, and I'm gonna type .show in it. And now, after I do this, you see the input car was this red car, and now we have a bunch of red cars as nearest neighbors. So this is really cool. In a few lines, we built an example of nearest neighbors for a car and for a cat. Emily and I really hope you've enjoyed the course so far. We've really explored the foundations of machine learning on a wide range of domains with a range of different applications, and really touched many of the practical issues around deploying and building machine learning systems. And now in this closing module, we're going to really summarize some of the concepts that we learned, talked about how to deploy these ideas, this machine learning systems in production, and then what's ahead in the specialization and in machine learning as a whole. Some really exciting stuff as we close off this first course. Now, so far, we've really just talked about, how do you build a machine learning model using data, how do you measure its quality, and how do you understand whether it's working or not. But that's not enough to build an intelligent application. When you build an intelligent application, you want to take that model that you learn and then really put it in front of, say, the customers of your company who are going to your website to buy a product. So what does that process actually look like? There are many different aspects associated with it. This is what we call model deployment, where we're taking the model and really allow it to serve predictions in real time. And we'll talk more about that. Then we have to talk about how do we evaluate that model to make sure what we did offline as we train the model is still good in the long run as we're using it. Then we have to think about all the management pieces. How do we make sure the model is still good? How do we replace it when the model improves? And how do we react to measurements that we make, which are actually the metrics that we monitor over time to try to understand whether our models are still good or it's time to relearn them from data. Now, all these pieces are really coming together. They're not just individual, separated ones, but all kind of interacting pieces that we need to understand deeply and create a cycle of improvement of the models that we have. So let's start with the first one. Let's start with the deployment piece. Now consider the following setup. You're building a really cool new kind of product recommender system, and you're using a bunch of data with millions of product reviews and users, and you want to take the model that you learned on your laptop or in your desktop or in a big cluster of machines and deploy it on a website that really interacts with your users. What does that look like? Well, that whole system starts with some historical data, some data that you've collected about the users of your system, the reviews they've written, what preferences they have, and we take that data and we feed it to train a model like we saw in the recommender systems module that Emily talked. That process with historical data is usually done in what's called a batch offline setting. You learn a model, say on your desktop machine or in a cluster. And then take that model and deploy it, for example, in the cloud, so that you can do what's called serving predictions. This is the online real-time part of the system. So for example, if you have a website, if this is what we're serving for, the website is going to give me information about my users, what they're doing right now, what pages they looked, what products they're thinking about buying. And then from that, we're gonna serve predictions in real time to say, oh, check out this giraffe, chew toy, remember that? Check that out, as this might be something that you wanna buy right now. Now, the user sees that giraffe offering, and they may or may not buy that giraffe. So that's the kind of feedback we're going to get back from the system. Did the user buy it or did they not buy it? And that's going to influence both our real-time decisions and go back to our historical data and really be collected in the long run so that we can improve our model as we collect more and more data from the world. So that's what a holistic deployment system for machine learning might look like.
Okay, so in this course, we've talked about lots of different machine learning methods and lots of applications where these types of methods can be very impactful. But of course, there are lots of open challenges that still remain in machine learning. So let's discuss some of them. One is the fact that we often have a choice of which model to use. So for example, when we talked about recommending products, we said we could use a classification model where we take features of the user and the product, pass it through this classifier, to say whether yes or no the person will like or not like this product. But then we also talked about using matrix factorization, where we were going to learn features about users and products and use that to recommend products to the users. And then we also talked about featureized matrix factorization, combining these two ideas. But the list often of possible models we can consider for tasks is very large. So typically this leaves the practitioner very perplexed. Which model should I use? And searching over this set of possible choices is still an open challenge in machine learning. Another really important challenge that we're often faced with is how do we represent our data? So for example, when we talked about our document modeling or document retrieval task, we said, well, we could use just raw word counts. Or we also talked about we could normalize the vectors. We could use things like TF-IDF to account for very popular words and to more emphasize the important words in the document. But honestly, there are lots of different variants of TF-IDF. We just provided one example of doing this. You could also think about using bigrams and trigrams, and there are lots and lots of ways we can think about representing the words that appear in a document. That's our data set of interest that we'd like to represent. But that's just for a document. Then maybe we have images. How do we represent an image? We've talked about some ways, we'll talk about others, but there's lots of challenges with that. Then maybe you have data that's really network-based, okay, things like from Facebook. So you can have very complicated data structures, and from very, very different diverse data sets, we want to be able to use the types of methods that we've described. So how we represent our data, of course, is going to have significant impact on the types of inferences that we make on that data. So this is a really, really important problem, and there's no one method for choosing the right representation of your data. One of the other really important and really significant challenges we're faced with in machine learning these days is how to scale up in multiple dimensions. So one aspect of this is the fact that data is getting bigger and bigger. So this is something that's been talked about extensively in the media. So let's just describe a few situations in which we're faced with a growing amount of data. One is the fact that there's just a large number of different platforms out there for social networking, collecting data via crowdsourcing and different things like this, sharing your photos, your videos, and reviewing restaurants, and the list of possible ways in which you can now go online and give data to the world is growing. And the amount of people doing this and providing data is just growing at this huge, huge rate. So we have lots of new data sources available to us. And in addition, the way we think about buying products, we no longer often just go to a store and have some handwritten record of what product was purchased. We now have vendors like Amazon who have these huge online marketplaces and collect data about different products and customers and the purchases being made, and lots of data from different sources like this. And beyond these types of websites, there's also a lot of devices that we can now wear. So there are these wearable devices. I can wear a watch that monitors all the activities I'm doing, how I'm sleeping at night. I can wear glasses that record everything that I'm seeing. I can also talk about the Internet of Things, which is just lots of connected devices and lots of different sources of information communicating with one another. So these are just some of the areas in which we're seeing lots and lots of new data sources. But of course, that's not exhaustive. We can also talk about things like medical records. Again, no longer do you go into your doctor's office and just have them write notes by hand that gets put in some file. Often they're taking electronic health records, and these are now communicating across systems. And we have lots and lots of electronic health records that it's just a source of data to be parsed and understood and used to innovate in medicine. So lots of new data sets, which is exciting. You know, we can learn a lot about how people operate, about our bodies, about how people purchase and make friends and how they go about their day-to-day activities. But of course, we need to have methods that scale to analyzing these types of data sets and also to the unique structure of data that's presented in these data sets and the noisy structure. And the list of challenges is really extensive. So this is one of the very big challenges in machine learning, is how to deal with this big data. And simultaneously to data being really large, we're also faced with a challenge with the fact that the models that we're using to analyze these increasingly complex data sets are also growing. So the models themselves are becoming bigger and more complicated in order to extract information from these ever-growingly, I don't know if that's a word, but you get my point, these very intricate data sources and very large data sources. So just as an example, when we talked about clustering, we talked about this application where you have recordings of brain activity taken over time. So this is just one quick example of a model that was used to analyze this type of data set. And without going into the details of what's shown here on this slide, just realize that there are lots of circles and lots of arrows. And what that means is that this is a really complicated, big model. So you might think, okay, well, data's getting bigger, models are getting bigger, but that's okay because processors are getting faster. Well, that was the story for a while. We were seeing this exponentially increasing rate of increased speed for our processors, but that stopped about a decade ago. And now what we're seeing is really very marginal increase in the speed of an individual processor. So instead, we have to think about new ways to scale up. And the typical thing that we're leveraging these days is collections of processors. And there are different architectures that we have. We have things like GPUs and multi-core and clusters and cloud computing resources and really fancy and expensive supercomputers. So that's great. Those are really powerful or potentially powerful computing resources that we have. But the question is, how do we use these in machine learning? And in machine learning, we have a number of challenges we're faced with. One is the fact that taking our machine learning algorithms and thinking about how to distribute them across these different processors and run everything we want to run in a coherent way is very challenging. Another challenge is, how do we distribute the data across these different machines? And how do we do all of this in a way that's very tolerant to different failures we can have of the individual machines? So these represent a number of challenges that we're facing in machine learning, and a lot of exciting research is coming out to start addressing these problems.